Hello there. I'm so glad you found your way here tonight. Right now, as you settle in, something remarkable is unfolding above you. A vast universe is quietly at work, spinning galaxies, igniting stars, and stretching the fabric of space itself with a patience you cannot fathom. Every photon of starlight, every distant supernova, every silent black hole is part of a cosmic symphony that has played for nearly 14 billion years. The universe is not a place you visit. It is a place you already are. It surrounds you constantly, like an ocean of space, holding you gently within its depths. Tonight, we journey into the quiet wonders of astronomy. We will explore over 100 soothing facts about the cosmos, from stars that explode with the power of entire galaxies to moons that hide oceans beneath frozen shells, from black holes that bend time to the ancient light that has traveled billions of years to reach your eyes. There is no test at the end, no rush, no urgency, just the gentle unfolding of cosmic wonders to carry you softly towards sleep. So let your breathing slow, let your thoughts grow quiet, and allow yourself to drift into the peaceful wonder of the universe that made you. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the remarkable processes happening across the cosmos. Either way, this space is for you. There is something deeply calming about contemplating the universe. Every star, every galaxy, every swirling nebula carries within it a story billions of years in the making. You are part of that story. The same atoms that form distant stars are also within you tonight. The carbon in your bones, the iron in your blood, the oxygen in your lungs were all forged in the hearts of ancient stars, scattered across space by unimaginable explosions. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in. Let the weight of the day drift away. And let us begin with the first of many quiet truths about astronomy. The universe is patient beyond measure. Stars form over millions of years. Galaxies collide over billions. Light travels for eons before reaching distant shores. And yet, within all that slowness, there are sudden bursts of wonder. Supernovae that outshine entire galaxies in an instant. Gamma-ray bursts that release more energy in seconds than the sun will in its entire lifetime. Black holes that swallow stars whole. Tonight, we will wander through this magnificent cosmos. We will meet the nebulae where stars are born. We will discover the moons that harbor hidden seas. And we will uncover truths about the universe that may surprise even the most curious minds. But there is no hurry. The cosmos has been unfolding since before the Earth existed. It can continue its quiet work while you rest. Let us begin with the wonders of the stars. Stars can explode with enough power to outshine entire galaxies. When a massive star reaches the end of its life, it can detonate in a supernova explosion so brilliant that it briefly outshines the combined light of every other star in its host galaxy. This single dying star for a few weeks radiates more energy than billions of suns burning steadily for years. The explosion occurs when the star's core can no longer support itself against gravity, triggering a catastrophic collapse followed by a rebound that blasts the outer layers into space. Supernovae come in different types, with the most powerful capable of creating shockwaves that travel through interstellar space for thousands of light-years. The elements forged in these explosions, including gold, silver, and uranium, are scattered across the cosmos to eventually become part of new stars, planets, and even living beings. Ancient civilizations recorded supernovae that appeared as new stars in the sky, visible even during daylight. These cosmic explosions are not just spectacular endings but also crucial beginnings, seeding the universe with the heavy elements necessary for rocky planets and life itself. Planets sometimes drift freely through space with no star to warm them. Scattered throughout the galaxy are rogue planets, worlds that wander alone through the darkness without any parent star to orbit. These lonely travelers may have formed around stars and been ejected through gravitational interactions with other planets. Or they may have formed directly from collapsing gas clouds like stars, but without enough mass to ignite nuclear fusion. Estimates suggest there could be billions of rogue planets drifting through the Milky Way alone, outnumbering the stars themselves. Without a star's warmth, these worlds exist in perpetual darkness, their surfaces frozen at temperatures close to absolute zero. Yet some may retain internal heat from radioactive decay or residual warmth from formation, potentially maintaining liquid water beneath thick icy crusts. The discovery of rogue planets has challenged our understanding of planetary formation, suggesting that the cosmos may be far more populated with wandering worlds than astronomers once imagined. These solitary travelers will continue their journeys through interstellar space for billions of years, occasionally passing through planetary systems before drifting back into the void. Black holes can spin so rapidly that they drag the very fabric of space around them. When a massive black hole rotates, it does not merely spin like a top, it actually drags the fabric of space and time around with it in a phenomenon called frame dragging. Near a rapidly spinning black hole, space itself is twisted into a vortex, carrying anything within it along for the ride, regardless of how that object is trying to move. This region, called the ergosphere, exists outside the event horizon and allows matter to be accelerated to tremendous speeds before either falling in or being flung away. Some black holes spin at nearly the speed of light, completing rotations in mere milliseconds, despite containing the mass of millions or billions of suns. The energy contained in this rotation is immense, and under certain conditions, some of it can be extracted and converted into powerful jets that shoot across space. Scientists measure black hole spin by observing the behavior of materials spiraling into them and the light emitted from their accretion disks. These spinning cosmic engines are among the most powerful objects in the universe. Beneath layers of ancient ice, certain moons hide oceans deeper than any found on Earth. Several moons in our solar system harbor vast oceans of liquid water beneath their frozen surfaces, containing more water than all of Earth's oceans combined. Europa, orbiting Jupiter, is believed to have a global ocean roughly twice the volume of all Earth's water, hidden beneath an icy shell perhaps 10 to 30 kilometers thick. Saturn's moon Enceladus shoots geysers of water ice into space from cracks near its south pole, revealing an underground sea heated by tidal forces. Ganymede, the largest moon in the solar system, may contain multiple layers of ocean, sandwiched between layers of ice at different pressures. These hidden seas remain liquid because tidal heating from the gravitational pull of their parent planets generates warmth deep within. The presence of liquid water, combined with potential chemical energy sources at the seafloor, makes these ocean moons prime candidates in the search for extraterrestrial life. Future missions aim to study these subsurface oceans more closely, potentially sending probes to sample the water beneath the ice. Galaxies can race toward one another at unbelievable speeds. Despite the overall expansion of the universe pushing most galaxies apart, gravity can override this expansion on local scales, pulling galaxies toward one another at tremendous velocities. The Milky Way and the Andromeda Galaxy are approaching each other at approximately 400,000 kilometers per hour, destined to collide in roughly 4 to 5 billion years. When galaxies merge, they do not crash like solid objects, but pass through each other in a gravitational dance lasting hundreds of millions of years. Stars rarely collide directly during these encounters because the spaces between them are so vast, but the gravitational interactions reshape both galaxies dramatically. Gas clouds do collide, triggering intense bursts of star formation that light up the merging system with brilliant blue young stars. The supermassive black holes at the centers of both galaxies will eventually spiral together and merge, releasing gravitational waves that ripple through the fabric of space-time. Such galactic collisions have been common throughout cosmic history and play a crucial role in building the largest galaxies we observe today. Some stars cool so dramatically that they begin to resemble giant planets. Brown dwarfs occupy a strange middle ground between the largest planets and the smallest stars. They form like stars from collapsing clouds of gas, but lack sufficient mass to sustain hydrogen fusion in their cores. Instead, they glow dimly from the heat of their formation and from temporary deuterium fusion before cooling over billions of years. The coolest brown dwarfs have surface temperatures lower than a candle flame, and some are cold enough that clouds of water ice may form in their atmospheres. At these temperatures, they emit almost no visible light, making them extraordinarily difficult to detect, despite potentially being numerous throughout the galaxy. Some brown dwarfs even have atmospheric chemistry similar to gas giant planets, with methane and ammonia present in their outer layers. The boundary between the largest gas giant planets and the smallest brown dwarfs remains fuzzy, distinguished primarily by how the object formed, rather than by any sharp physical divide. These failed stars will continue cooling for trillions of years, eventually becoming cold, dark objects drifting invisibly through space. Comets often carry organic molecules that formed long before the Sun existed. Comets are frozen time capsules preserving material from the earliest days of the solar system, and even earlier. These icy bodies carry complex organic molecules, including amino acids and other building blocks of life, that formed in the cold, dark molecular cloud that eventually collapsed to create our Sun. When spacecraft have analyzed comet dust and gas, they have found a rich inventory of organic compounds, some of which could have contributed to the origin of life on Earth. The ice in comets has remained largely unchanged for over 4.5 billion years, offering scientists a glimpse into the chemical conditions that existed when the solar system was forming. As comets approach the Sun, they develop glowing tails as ice sublimates and releases trapped dust and gas, creating the spectacular displays that have awed humans throughout history. Some theories suggest that comets delivered water and organic material to early Earth, helping to create the conditions necessary for life to emerge. These ancient wanderers continue to orbit the Sun, occasionally visiting the inner solar system before returning to the cold outer reaches. Nebulae can glow fiercely when newborn stars flood them with intense radiation. Emission nebulae are among the most beautiful objects in the night sky, vast clouds of hydrogen gas that glow with vibrant colors when energized by the ultraviolet radiation of hot young stars embedded within them. The energetic photons strip electrons from hydrogen atoms, and when these electrons recombine, They emit light at specific wavelengths that create the characteristic red and pink hues of these cosmic clouds. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is one of the closest stellar nurseries to Earth and showcases this process beautifully. Within these glowing clouds, new stars continually form from denser regions that collapse under gravity, perpetuating the cycle of illumination. The shapes of emission nebulae are sculpted by stellar winds and radiation pressure from the hottest stars, creating pillars, globules, and intricate structures that change over thousands of years. These nebulae do not last forever, as their gas is consumed by star formation or blown away by stellar winds. They gradually fade. What remains are the stars they birthed, now scattered across space. Extreme gravitational forces can stretch planets into elongated, egg-like shapes. When a planet orbits very close to its host star, or when a moon orbits close to a giant planet, tidal forces can distort the body into an elongated, egg-like shape, rather than a perfect sphere. These forces arise because gravity is stronger on the side of the body, closer to the massive object, creating a stretching effect across the diameter. Jupiter's moon Io experiences such intense tidal squeezing that its interior is constantly flexed, generating enough heat to power the most active volcanoes in the solar system. Some exoplanets orbit so close to their stars that they are stretched significantly, with their closest face pulled toward the star while their far side bulges outward. This constant flexing can generate enormous amounts of internal heat, contributing to geological activity far beyond what the body's size alone would suggest. In extreme cases, if an object ventures too close to a black hole or neutron star, tidal forces can tear it completely apart in a process called tidal disruption. The shapes of many moons and planets throughout the cosmos testify to the power of gravity to mold and stretch worlds. Pulsars emit perfectly timed beams of radiation that sweep the sky like cosmic lighthouses. Pulsars are rapidly spinning neutron stars that emit beams of radio waves, X-rays, or even gamma rays from their magnetic poles. As the neutron star rotates, these beams sweep through space like the rays of a lighthouse, and if Earth happens to lie in the path of the beam, we detect a pulse of radiation with each rotation. Some pulsars spin hundreds of times per second, their pulses arriving with a regularity that rivals the most precise atomic clocks. This remarkable precision has made pulsars useful for a variety of scientific applications, from testing theories of gravity to potentially serving as a galactic navigation system for future spacecraft. Pulsars form in the aftermath of supernova explosions, when the core of a massive star collapses to form an incredibly dense object just a few kilometers across, but containing more mass than the Sun. The intense magnetic fields of pulsars, trillions of times stronger than Earth's, channel radiation along the poles and accelerate particles to tremendous energies. Over millions of years, pulsars gradually slow their rotation as they lose energy, eventually fading into silence. Gas giant planets can brew storms larger than Earth that refuse to fade. The atmospheres of gas giant planets host colossal storm systems that dwarf anything found on Earth, and can persist for decades or even centuries. Jupiter's Great Red Spot is the most famous example, a swirling anticyclone large enough to contain 2 or 3 Earths that has been raging for at least several centuries. Winds at the edges of this storm reach speeds exceeding 600 kilometers per hour, circulating around a relatively calm central eye. Saturn hosts its own periodic megastorms that erupt roughly every 30 Earth years, encircling the entire planet with bands of churning cloud. The energy driving these storms comes partly from internal heat radiating outward from the planet's core, combined with energy absorbed from sunlight. Unlike hurricanes on Earth, which dissipate when deprived of warm ocean water. These giant planet storms have no solid surface to slow them down, and can sustain themselves indefinitely. Neptune, despite its great distance from the Sun and frigid temperatures, shows some of the fastest winds in the solar system, driving enormous dark spots across its blue atmosphere. Entire galaxies sometimes form with so few stars that they appear almost empty. Ultra-diffuse galaxies are ghostly collections of stars spread so thinly across space that they contain far fewer visible stars than typical galaxies of similar size. Despite being as wide as the Milky Way, these phantom galaxies may contain only a fraction of 1% as many stars, making them extremely difficult to detect against the darkness of space. Many ultra-diffuse galaxies appear to be held together primarily by dark matter, with the visible stars representing only a tiny fraction of the total mass. How these galaxies formed remains a mystery, with theories suggesting they may be failed galaxies that ran out of gas before forming many stars, or normal galaxies that were puffed up by some energetic process. Some ultra-diffuse galaxies orbit within clusters of larger galaxies, while others drift in isolation through the cosmos. Their discovery has expanded our understanding of how varied galaxy formation can be. These dim, ghostly systems may be far more common than previously thought, hiding in the spaces between brighter galaxies throughout the universe. A stellar remnant can shrink to the size of Earth while becoming incredibly dense. When a medium-sized star like our Sun exhausts its nuclear fuel, its core collapses into a white dwarf, an object roughly the size of Earth, but containing nearly the mass of an entire star. The density of white dwarf material is so extreme that a single teaspoon would weigh several tons on Earth. No nuclear fusion occurs in the core. Instead, the white dwarf is supported against further collapse by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too closely together. These stellar corpses begin their existence glowing brightly from leftover heat but gradually cool over billions of years, eventually fading to become cold, dark black dwarfs. White dwarfs represent the final evolutionary stage for the vast majority of stars in the universe, including our own Sun approximately 5 billion years hence. Some white dwarfs in binary systems can acquire material from companion stars, occasionally triggering thermonuclear explosions on their surfaces, or even complete detonation of the entire star. These explosions, called Type Ia supernovae, serve as crucial cosmic distance markers for astronomers. Planetary systems occasionally develop with planets orbiting at impossible-looking angles. While our solar system features planets orbiting roughly in the same plane and direction, many exoplanetary systems exhibit far more chaotic arrangements. Some planets orbit their stars at highly tilted angles, while others travel on retrograde orbits, moving opposite to their star's rotation. Hot Jupiters, gas giants that have migrated extremely close to their stars, sometimes orbit at angles nearly perpendicular to the stellar equator. These bizarre configurations likely result from gravitational interactions between planets, or between planets and passing stars, flinging worlds onto dramatically altered trajectories. In some multi-planet systems, the orbital planes of different planets can differ by tens of degrees, creating a three-dimensional arrangement quite unlike our orderly solar system. The discovery of these tilted and misaligned systems has revolutionized our understanding of how planetary systems evolve over time. What appears impossible at first glance is simply the natural result of gravitational chaos operating over millions of years. Our solar system's relative flatness appears to be fortunate rather than inevitable. Metal-rich asteroids can hold more precious material than Earth's entire crust. Some asteroids are composed primarily of iron and nickel, along with smaller amounts of precious metals like gold, platinum, and rare earth elements that accumulated during the formation of the solar system. A single metallic asteroid a kilometer or two across could contain more platinum group metals than have ever been mined in human history. These cosmic treasure troves are thought to be the exposed cores of ancient planetesimals that were differentiated by internal heating before being shattered in collisions. The asteroid Psyche, one of the largest metallic asteroids in the belt between Mars and Jupiter, may be the remnant core of a failed planet and is the target of an upcoming NASA mission. The concentration of valuable metals in asteroids is far higher than in typical terrestrial ores, where they are diluted by surrounding rock. While asteroid mining remains technologically challenging, the potential resources represented by these metallic bodies have captured the imagination of scientists and entrepreneurs alike. Understanding the composition of metallic asteroids also provides insights into the internal structure of the rocky planets, including Earth. Massive stars burn through their fuel so quickly that their lives end in an instant compared to cosmic time. The most massive stars in the universe live fast and die young, consuming their nuclear fuel at prodigious rates and exhausting their cores in just a few million years. While a star like our Sun will shine steadily for approximately 10 billion years, a star with 50 times the Sun's mass may burn through its hydrogen in only a few million years, before evolving rapidly through subsequent fusion stages. These stellar giants are so luminous that they can be seen across vast distances, their brilliant blue light dominating the regions where they form. The pressure and temperature at their cores are so extreme that they fuse heavier and heavier elements in successive shells, building up layers like an onion, until an iron core forms. When fusion can no longer support the core, the star collapses catastrophically and rebounds in a supernova explosion that scatters the synthesized elements across space. The rarity of massive stars compared to smaller ones reflects both their rapid evolution and the physics of star formation. Despite their short lives, massive stars contribute disproportionately to the chemical enrichment of galaxies. Some planets reflect so much starlight that they shine like tiny suns. Certain exoplanets orbiting extremely close to their host stars reflect a surprising amount of light, making them among the brightest planets relative to their stars yet discovered. These highly reflective worlds often have atmospheric conditions that create clouds of reflective particles, such as silicates or metallic compounds, that bounce starlight back into space. The reflectivity, or albedo, of a planet depends on its atmospheric composition, cloud coverage, and surface properties. Some hot Jupiters appear to have mirrored atmospheres that reflect more light than any world in our solar system. In contrast, other exoplanets absorb nearly all incoming starlight, appearing darker than charcoal despite their extreme temperatures. The study of exoplanet reflectivity helps astronomers understand atmospheric chemistry and cloud formation in alien worlds. As observational techniques improve, scientists are beginning to map the reflectivity of exoplanet surfaces and atmospheres, revealing diversity far beyond what we see in our own solar system. These shining worlds serve as beacons that help astronomers detect and characterize distant planetary systems. Certain regions of space contain magnetic fields millions of times stronger than Earth's. Neutron stars and magnetars possess the most powerful magnetic fields known to exist, reaching strengths trillions of times greater than the magnetic field of our planet. A magnetar's field is so intense that it would distort the electron clouds of atoms, fundamentally altering the chemistry of any matter within its influence. At a distance of 1,000 kilometers from a magnetar, the magnetic field would be strong enough to erase the magnetic strip on every credit card on Earth and potentially be lethal to humans. These extreme fields are created during the collapse of massive star cores into neutron stars, with the original magnetic field of the star compressed into a tiny volume. Magnetar fields decay over thousands of years, but during their active phase they can power tremendous bursts of X-rays and gamma rays. Even ordinary pulsars, while not as extreme as magnetars, possess fields millions of times stronger than any magnet humans have ever constructed. The physics of matter under such extreme magnetic conditions remains an active area of research. Galaxy clusters can bend and stretch distant starlight into graceful luminous arcs. The immense gravitational pull of galaxy clusters can bend light passing through them, acting as cosmic magnifying glasses that distort and amplify the images of more distant galaxies behind them. This phenomenon, called gravitational lensing, was predicted by Einstein's general theory of relativity and has become a powerful tool for astronomers. When a distant galaxy happens to lie almost directly behind a massive cluster, its light can be bent into beautiful arcs, or even multiple images arranged around the cluster. These arcs are stretched and magnified images of galaxies billions of light-years away that would otherwise be too faint to observe. By studying the distortions, astronomers can map the distribution of both visible and dark matter in the lensing cluster. Some of the most distant and faintest objects ever observed have been revealed through gravitational lensing, allowing glimpses into the early universe. The elegant curves of lensed galaxies remind us that space itself is flexible, shaped by the mass it contains in ways that Einstein first described over a century ago. Dying stars sometimes release gas in complex shapes that look sculpted by hand. Planetary nebulae are the beautiful remnants of medium-sized stars like our Sun, glowing shells of gas expelled during the final stages of stellar evolution. Despite their name, they have nothing to do with planets. Early astronomers coined the term because some appeared round and planet-like through small telescopes. Modern observations have revealed an astonishing variety of shapes, from spherical shells to hourglasses, butterflies and spirals, many displaying intricate symmetry that seems almost designed. These complex structures arise from interactions between fast stellar winds, slower earlier ejections, magnetic fields, and binary companions that shape the expanding gas. The central star, now a hot white dwarf, floods the nebula with ultraviolet light that causes the gas to glow in vivid colors, with different elements producing different hues. Planetary nebulae last only a few tens of thousands of years before dispersing into the interstellar medium, enriching it with elements produced during the star's lifetime. The Hubble Space Telescope has captured stunning images of these cosmic artworks, revealing details invisible from Earth's surface. Star-forming clouds can collapse under their own gravity to create entire families of new suns. Giant molecular clouds are vast reservoirs of gas and dust, where stars are born in groups, sometimes producing thousands of stellar siblings from a single collapsing region. These stellar nurseries can span hundreds of light-years and contain enough material to form millions of stars. When parts of these clouds become dense enough, gravity overwhelms the pressure that keeps them expanded, and they begin to collapse, fragmenting into smaller clumps that each form individual stars or multiple star systems. The process is often triggered by external events, such as the shock wave from a nearby supernova, or the compression caused by spiral arm passage. Stars born from the same cloud share similar chemical compositions and ages, but may scatter across the galaxy over millions of years, as gravitational interactions disperse them. Open clusters like the Pleiades represent young stellar families, still loosely bound together, though even these will eventually dissolve. Our own Sun likely formed in such a cluster approximately 4.5 billion years ago. with its siblings now scattered throughout the Milky Way, perhaps dozens of light-years apart. Planetary orbits can evolve into strange elongated shapes after gravitational encounters. While planets typically form on nearly circular orbits, gravitational interactions can gradually stretch these paths into highly elliptical shapes that carry worlds much closer to and farther from their stars. In some exoplanetary systems, planets follow orbits more elongated than comets in our solar system, experiencing radical temperature changes as they swing between close approaches and distant retreats. These eccentric orbits often result from gravitational interactions between multiple planets, where close encounters can transfer energy and angular momentum in dramatic ways. Some planets have been found on orbits so elongated that they spend most of their time in the frozen outer reaches of their systems before plunging close to their stars in brief scorching passages. The gravitational influence of passing stars can also perturb planets onto eccentric paths over millions of years. Mercury in our own solar system has the most eccentric orbit of the major planets, though its path is mild compared to some exoplanetary extremes. Understanding how orbits become eccentric helps astronomers reconstruct the violent histories of planetary systems. Black hole jets can shoot particles across distances larger than their host galaxies. Some supermassive black holes at the centers of galaxies launch powerful jets of plasma that extend far beyond the visible boundaries of their host galaxies, reaching distances of hundreds of thousands or even millions of light-years. These jets are formed when material falling toward a black hole is accelerated and collimated by intense magnetic fields, shooting outward at close to the speed of light. The energy contained in these jets is staggering, equivalent to the total luminosity of trillions of stars, sustained over millions of years. As the jets plow through intergalactic space, they create enormous lobes of radio-emitting plasma that can be detected by radio telescopes on Earth. The jets can heat and push aside gas that would otherwise fall into the galaxy, effectively regulating how many new stars can form. This feedback between the central black hole and its host galaxy plays a crucial role in shaping how galaxies evolve over cosmic time. Some jets appear to point almost directly at Earth, creating blazes that are among the brightest objects in the universe. Some moons experience tidal heating strong enough to melt rock deep underground. Tidal heating occurs when gravitational forces from a parent planet and neighboring moons continuously flex and squeeze a world, generating heat through friction within its interior. Jupiter's moon Io is the most volcanically active body in the solar system, with hundreds of volcanoes constantly erupting due to the intense tidal forces exerted by Jupiter and the orbital resonance with neighboring moons Europa and Ganymede. The surface of Io is constantly reshaped by lava flows, volcanic plumes, and the deposition of sulfur compounds that give it its distinctive yellow and orange coloration. Saturn's moon Enceladus demonstrates the power of tidal heating on a smaller scale, with geysers shooting water ice and vapor into space from fractures near its south pole. This mechanism is crucial for maintaining the liquid water oceans believed to exist beneath the icy surfaces of several outer solar system moons. Without tidal heating, these distant worlds would be frozen solid, but instead they may harbor environments potentially suitable for life. The intensity of tidal heating depends on orbital eccentricity, the proximity to the parent planet, and the internal structure of the moon itself. Ancient starlight can travel across the cosmos for billions of years before reaching Earth. When you look at a distant galaxy, you are seeing light that began its journey long before Earth or even our Sun existed. Light travels at approximately 300,000 kilometers per second, an incredible speed that seems instantaneous on human scales, but reveals vast time delays across cosmic distances. The most distant objects observable from Earth emitted their light over 13 billion years ago, when the universe was less than 1 billion years old. This means astronomers can literally look back in time, observing the universe as it was in its youth, by studying the most distant galaxies. Light from the Andromeda Galaxy, our nearest large galactic neighbor, takes approximately 2.5 million years to reach us, so we see that galaxy as it was when early human ancestors roamed the Earth. Even starlight from within our own Milky Way takes tens of thousands of years to traverse the galaxy's extent. This cosmic time delay transforms telescopes into time machines, allowing us to study the evolution of galaxies, stars, and the universe itself. Dust-filled nebulae can hide fully formed stars behind thick veils of shadow. Dark nebulae are dense clouds of dust and gas that block the light of stars lying behind them, creating silhouettes against brighter backgrounds. These cosmic shadows can take on striking shapes, like the famous Horsehead Nebula in Orion, which appears as a dark profile against a glowing curtain of hydrogen gas. The dust grains within these clouds are typically smaller than a micrometer, made of silicates and carbon compounds that efficiently absorb and scatter visible light. Despite blocking optical light, dark nebulae can be penetrated by infrared radiation, which has longer wavelengths that pass more easily through the dust. Infrared telescopes have revealed that these apparently empty voids are actually teeming with young stars and protostars still forming deep within the obscured regions. Dark nebulae often represent the densest parts of larger molecular clouds, the very regions where gravity is strongest and star formation is most active. What appears as emptiness in visible light is actually among the most productive star-forming real estate in the galaxy. Violent stellar winds can strip atmospheres away from vulnerable planets. Stars emit continuous streams of charged particles called stellar winds that flow outward through their planetary systems at speeds of hundreds of kilometers per second. For planets without strong magnetic fields, or that orbit very close to their stars, these winds can gradually erode and strip away atmospheric gases. Mars, with its weak magnetic field and low gravity, has lost much of its original atmosphere to the solar wind over billions of years, transforming it from a potentially habitable world to the cold desert we see today. Exoplanets orbiting very close to active stars face even more intense bombardment, with some losing substantial portions of their atmospheres over their lifetimes. Young stars are particularly active, with stellar winds and radiation far more powerful than our current sun's output, potentially sterilizing or stripping nascent planetary atmospheres. The habitability of any Earth-like planet depends critically on its ability to retain an atmosphere against this constant erosion. Magnetic fields like Earth's create protective magnetospheres that deflect much of the solar wind, allowing our atmosphere to persist despite billions of years of exposure. High-energy radiation from massive stars can sculpt nearby clouds into towering pillars. The famous Pillars of Creation in the Eagle Nebula represent one of the most iconic examples of how stellar radiation shapes the cosmic landscape. These finger-like projections of gas and dust extend several light-years in length, their surfaces being eroded by intense ultraviolet radiation from nearby hot stars. The radiation evaporates the outer layers of gas in a process called photoevaporation, while denser clumps resist longer and protect the material behind them, creating the elongated pillar shapes. At the tips of these pillars, small dense knots called evaporating gaseous globules may contain protostars forming in the shadow of the eroding cloud. Similar pillars and elephant trunk structures appear in star-forming regions throughout the galaxy, wherever massive stars illuminate nearby gas clouds. The sculpting process simultaneously destroys the clouds, while also potentially triggering new star formation by compressing material at the pillar surfaces. Over hundreds of thousands of years, the radiation will completely evaporate these structures, exposing any young stars that manage to form within. Magnetic fields in space can twist and confine blazing streams of charged particles. Throughout the cosmos, magnetic fields channel and control the movement of electrically charged particles, creating structures ranging from planetary radiation belts to the jets streaming from black holes. When charged particles encounter magnetic field lines, they spiral around them, unable to cross perpendicular to the field direction. This confinement creates well-defined structures like Earth's Van Allen belts, where high-energy particles are trapped in donut-shaped regions surrounding our planet. Around pulsars and magnetars, magnetic fields billions of times stronger than Earth's focus particles, to tremendous energies and direct beams of radiation along the magnetic poles. In jets from active galactic nuclei, helical magnetic fields confine plasma into narrow columns that maintain their coherence across millions of light-years. The magnetic fields themselves originate from the movements of charged particles, creating a complex interplay between field and matter. Understanding cosmic magnetic fields is challenging because they are invisible except where they interact with matter, requiring indirect measurements through polarization and particle behavior. Planetary collisions can reshape entire worlds in a single catastrophic moment. The violent impacts between planetary bodies have shaped the solar system from its earliest days, and such collisions continue to influence planetary evolution throughout the cosmos. The prevailing theory for the Moon's formation holds that a Mars-sized body struck the early Earth approximately 4.5 billion years ago, blasting debris into orbit that eventually coalesced into our natural satellite. Uranus may have been knocked onto its extreme axial tilt by an ancient impact with a large planetesimal, causing it to roll around the Sun on its side. Mercury's unusually large core relative to its mantle might result from an early collision that stripped away much of its outer layers. Observations of dust around other stars suggest that planetary collisions occur in distant systems as well, with infrared signatures revealing the debris of worlds that have recently shattered. These violent events, while destructive, also mix materials between bodies and can fundamentally alter planets, rotations, compositions, and even potential habitability. The cratering visible on nearly every solid surface in the solar system testifies to the ongoing bombardment that all worlds experience. Rings around distant planets can stretch wider than the distance between Earth and the Moon. Planetary ring systems, like those of Saturn, are among the most beautiful structures in our solar system, comprised of countless individual particles, ranging from tiny grains to house-sized boulders. Saturn's rings span roughly 270,000 kilometers in diameter, roughly 70% of the distance from Earth to the Moon, though they are remarkably thin, averaging only about 10 meters in vertical extent. Ring systems form from material that never coalesced into moons, or from moons that were torn apart by tidal forces when they ventured too close to their parent planet. Each particle in a ring system orbits independently, with inner particles traveling faster than outer ones, creating the banded appearance we observe. Jupiter, Uranus, and Neptune also possess ring systems, though much fainter and more tenuous than Saturn's iconic bands. Beyond our solar system, large ring systems may exist around exoplanets and even around moons, though detecting them remains challenging with current technology. Some proposed exoplanet rings could be vastly larger than Saturn's, potentially visible during transits, as additional dips in stellar brightness. Some stars orbit each other so closely that they share outer layers of gas. Contact binary stars are stellar pairs, orbiting so close together that their outer atmospheres touch and merge, creating a peanut-shaped or dumbbell-shaped system enveloped in a common gaseous envelope. In these intimate configurations, material can flow between the stars, with the more massive component often stealing gas from its companion and growing larger over time. The orbital periods of contact binaries can be remarkably short, sometimes just a few hours, as the stars whirl around their common center of mass at close range. This mass transfer can have dramatic consequences, including novae eruptions when hydrogen accumulates on a white dwarf until it explosively ignites in a thermonuclear flash. The extreme proximity means these stars influence each other's evolution dramatically, and they may eventually merge into a single, more massive star in a spectacular stellar collision. Over-contact binaries like W Ursae Majoris systems are common in our galaxy, and their study helps astronomers understand how mass transfer and stellar mergers shape stellar populations. Some of these systems may eventually produce exotic objects like blue stragglers, stars that appear younger than their true age due to mass gained from companions. Dense globular clusters can pack hundreds of thousands of stars into tight spheres. Globular clusters are ancient spherical collections of stars, gravitationally bound together in compact configurations that can contain anywhere from tens of thousands to over 1 million stars. These clusters orbit the centers of galaxies in the galactic halo, relics from the earliest epochs of galaxy formation over 10 billion years ago. The stars within globular clusters are typically old, red, and low in heavy elements, reflecting the composition of the universe when they formed, before many generations of stars had enriched the cosmos with heavier atoms. Near the cores of dense globular clusters, stars can be so tightly packed that stellar encounters and collisions become relatively common, potentially forming exotic objects like blue stragglers and binary pulsars. The Milky Way hosts roughly 150 known globular clusters, each one a gravitationally bound fossil of our galaxy's distant past. Studying globular clusters has helped astronomers understand the age of the universe and the structure of our galaxy, as their positions trace the spherical halo rather than the flat disk. Some globular clusters may even be the stripped cores of dwarf galaxies consumed by the Milky Way long ago. The interstellar medium can carry shock waves from ancient supernova explosions. When massive stars explode as supernovae, they send powerful shock waves racing through the interstellar medium at thousands of kilometers per second, sweeping up and compressing gas as they expand. These supernova remnants can persist for hundreds of thousands of years, gradually cooling and slowing as they interact with surrounding material. The shock waves heat gas to millions of degrees, causing it to emit X-rays that reveal the remnant structure to space telescopes. As the shock wave plows through the interstellar medium, it compresses gas clouds that might otherwise have remained diffuse, potentially triggering the formation of new stars from the compressed material. The expanding shock also distributes heavy elements forged in the supernova throughout the galaxy, seeding future generations of stars and planets with the building blocks for rocky worlds and life. Multiple overlapping supernova remnants can create superbubbles, enormous cavities in the interstellar medium spanning hundreds of light years. Our own solar system resides within one such structure called the local bubble, carved out by supernova that exploded roughly 10 to 20 million years ago. Some planets orbit so rapidly that their years last only a few Earth days. Ultra-short period planets are exotic worlds that complete an entire orbit around their stars in less than a day, subjected to extreme temperatures and gravitational stresses. These planets orbit so close to their host stars that their surfaces can reach temperatures exceeding 2000 degrees, hot enough to vaporize rock and metal. At such close distances, the gravitational pull from the star creates enormous tidal forces that may keep one face of the planet permanently locked toward the star in a scorching eternal day. Some ultra-short period planets are thought to be the remnants of hot Jupiters that migrated inward and gradually lost their atmospheres to stellar radiation, leaving behind dense, rocky, or metallic cores. The TESS and Kepler missions have discovered numerous examples of these extreme worlds, revealing that tight orbits are surprisingly common among exoplanets. Planets in such close orbits may slowly spiral inward due to tidal interactions, eventually being consumed by their stars over millions or billions of years. Studying these extreme worlds helps astronomers understand the diversity of planetary outcomes and the physical limits of planetary survival. Spiral galaxies can grow new arms as they interact with neighboring systems. When galaxies pass close to one another, their mutual gravitational forces can distort their shapes, stretching and pulling stars and gas into new configurations, including extended spiral arms and tidal tails. These gravitational interactions can trigger waves of compression that propagate through the galactic disk, enhancing existing spiral structure or generating new arms where none existed before. The density waves associated with spiral arms are particularly effective at triggering star formation, as gas clouds are compressed as they pass through the arms. Some of the most dramatic spiral arms occur in galaxies currently interacting with neighbors, like the Whirlpool galaxy, whose prominent arms are enhanced by its ongoing encounter with a smaller companion. Even distant neighbors can influence spiral structure over hundreds of millions of years, with repeated close passages gradually shaping the appearance of both systems. The Milky Way's own spiral structure may have been influenced by interactions with the Large and Small Magellanic Clouds and by ancient mergers with dwarf galaxies. As galaxies fall together, their spiral arms often become more pronounced, before eventually being disrupted completely during the final merger stages. Massive star clusters can light up the surrounding gas with intense ultraviolet radiation. Young massive star clusters contain some of the hottest and most luminous stars in existence, which flood their surroundings with intense ultraviolet radiation that ionizes nearby hydrogen gas. The resulting emission nebulae glow brilliantly in the red light of hydrogen alpha emission, creating the spectacular star-forming regions visible throughout our galaxy and beyond. The most massive stars in these clusters are O-type and B-type giants that burn through their nuclear fuel rapidly but shine with tremendous intensity during their brief lifetimes. The radiation from a single young cluster can illuminate a region spanning tens of light years, creating vast bubbles of ionized gas surrounding the stars. Within these bubbles, the intense radiation sculpts the surrounding gas into pillars, globules, and elephant trunk structures, where denser material resists evaporation. The ultraviolet light also drives powerful winds that clear paths through the natal cloud, eventually dispersing enough material to reveal the newly formed cluster. These clusters serve as cosmic laboratories for studying the most energetic stellar processes and the interaction between massive stars and their environments. Rogue stars can travel at immense speeds through intergalactic space. Hypervelocity stars are stellar outcasts, hurtling through space at speeds exceeding hundreds of kilometers per second, fast enough to escape the gravitational pull of their home galaxies entirely. These speeding stars are believed to be ejected through interactions with supermassive black holes at galactic centers, where the extreme gravity can slingshot one star outward while capturing a companion. When a binary star system approaches too close to a supermassive black hole, one star may be captured into orbit while its companion is flung away at tremendous velocity. Some hypervelocity stars have been found moving at over 1,000 kilometers per second relative to the Milky Way, trajectories that will carry them into intergalactic space, never to return. Other mechanisms can also produce high-velocity stars, including asymmetric supernova explosions that kick the surviving remnant or companion in a particular direction. These cosmic wanderers carry information about their origins, allowing astronomers to trace their paths back to their birthplaces and study conditions near galactic centers. Once ejected into intergalactic space, hypervelocity stars will journey alone through the cosmic void for billions of years. Some planetary systems form multiple asteroid belts that resemble cosmic rings. While our solar system hosts a single main asteroid belt between Mars and Jupiter, some exoplanetary systems appear to possess multiple belts at different distances from their stars. These additional belts are detected through the infrared glow of dust produced by collisions between asteroids, which absorbs starlight and re-emits it at longer wavelengths. Systems like Epsilon Eridani show evidence of multiple debris belts, suggesting complex planetary architectures that have sculpted material into separate rings at different orbital distances. The presence and location of asteroid belts provide clues about unseen planets, since gravitational resonances with planets clear certain regions while concentrating material in others. In our own system, Jupiter's gravity both maintains the asteroid belt and prevents that material from coalescing into a planet. Multiple belt systems may indicate multiple large planets at different distances, each carving out gaps and shepherding debris into stable configurations. Studying these dusty disks around other stars helps astronomers understand the diversity of planetary system architectures and the processes that shape them over billions of years. Quasars can shine with the power of trillions of stars combined. Quasars are among the most luminous objects in the known universe, powered by supermassive black holes actively devouring vast quantities of gas and dust at the centers of distant galaxies. As material spirals into these black holes, it forms a swirling accretion disk that heats to millions of degrees and radiates enormous amounts of energy across the electromagnetic spectrum. A single quasar can outshine its entire host galaxy by a factor of hundreds, blazing bright enough to be visible across billions of light-years. The first quasars were discovered in the 1960s as mysterious point-like objects with extremely redshifted spectra, indicating enormous distances that implied unimaginable luminosities. At their peak activity in the early universe, quasars were far more common, representing a violent epoch when young galaxies were gas-rich and black hole feeding was at its height. Modern observations have resolved the host galaxies around nearby quasars, confirming that these luminous beacons reside at the hearts of otherwise normal-looking galaxies. The most distant known quasars shine from when the universe was less than 1 billion years old, illuminating conditions in the cosmic dawn. The surfaces of some moons are constantly reshaped by cryovolcanic eruptions. Cryovolcanism is a process similar to volcanic activity on Earth, except that the erupting materials are volatiles like water, ammonia or methane, rather than molten rock. On icy moons in the outer solar system, internal heat from tidal forces or radioactive decay can melt subsurface ices, which then erupt onto the surface as slushy flows or explosive geysers. Triton, Neptune's largest moon, shows evidence of past cryovolcanic activity, with smooth plains that appear to have been resurfaced by flows of icy material. Saturn's moon Enceladus actively ejects plumes of water vapor and ice particles from fractures near its south pole, creating a constant source of fresh material that feeds Saturn's diffuse E-ring. Titan, Saturn's largest moon, may also host cryovolcanic features, though its thick atmosphere makes surface observations challenging. These icy eruptions carry material from subsurface oceans to the surface, potentially providing opportunities to sample internal environments without drilling. Cryovolcanism makes these outer solar system moons dynamic worlds, rather than the frozen wastelands they might otherwise appear to be. Gravitational lensing can magnify galaxies so distant that they would otherwise be invisible. Massive objects like galaxy clusters can act as cosmic magnifying glasses, bending and amplifying light from more distant sources through the phenomenon of gravitational lensing. When a background galaxy happens to be aligned behind a foreground cluster, its light can be magnified by factors of tens or even hundreds, revealing details that would otherwise be far too faint to observe. This natural magnification allowed astronomers using the James Webb Space Telescope to detect some of the most distant galaxies ever observed, ancient systems from when the universe was only a few 100 million years old. The distorted images created by lensing can appear as arcs, rings, or multiple copies of the same background object stretched around the lensing mass. By analyzing these distortions, astronomers can map the distribution of mass in the foreground cluster, including the invisible dark matter that dominates its gravitational influence. Gravitational lensing has become an essential tool for studying the early universe, effectively turning massive clusters into nature's own telescopes. Without this cosmic magnification, many of the most distant and faintest objects known would remain forever beyond our reach. Young stars can flicker unpredictably as dust clouds drift across our line of sight. T-Tauri stars and other young stellar objects often display erratic brightness variations as clumps of dust and gas in their surrounding disks pass between the star and our telescopes. These variations can occur on timescales from hours to years, depending on the size and orbital distance of the obscuring material. Some young stars experience dramatic dimming events when dense material temporarily blocks much of their light, only to brighten again as the obscuration passes. The complexity of the protoplanetary disk environment, with its spiral arms, gaps, and embedded protoplanets, creates constantly changing silhouettes against the stellar light. Beyond simple occultation, young stars also exhibit intrinsic variability from magnetic activity, accretion events, and other processes related to their ongoing formation. The star KIC 8,462,852, famously known as Boyajian's star, displayed bizarre dimming patterns that initially defied explanation before being attributed to dust. Monitoring young star variability helps astronomers understand the structure and dynamics of planet-forming disks, revealing the environments where new worlds are taking shape. Some galaxies grow by steadily consuming smaller companions. Galactic cannibalism is the process by which larger galaxies gravitationally capture and absorb smaller neighbors, gradually adding their stars, gas, and dark matter to their own bulk. The Milky Way is currently in the process of consuming several dwarf galaxies, including the Sagittarius dwarf elliptical galaxy, which is being stretched and torn apart by our galaxy's tidal forces. Streams of stars trailing from these disrupted companions wrap around the Milky Way like cosmic debris trails, marking the paths of galaxies that are no longer intact. This process of hierarchical assembly is a fundamental aspect of how galaxies grow over cosmic time, with smaller structures merging to form larger ones. The Milky Way itself will eventually merge with the Andromeda Galaxy in approximately 4.5 billion years, creating a larger elliptical galaxy sometimes called Milkomeda. Evidence of past mergers can be found in the orbits of stars that move differently from the main galactic population, remnants of galaxies we absorbed long ago. Computer simulations show that galaxies like our own have consumed dozens of smaller systems throughout their histories. The atmospheres of some exoplanets glow faintly as they heat up in starlight. Hot Jupiters and other close-orbiting exoplanets absorb intense radiation from their nearby stars, heating their atmospheres to temperatures exceeding 1,000 degrees and causing them to glow in infrared wavelengths. This thermal emission can be detected when the planet passes behind its star, as the combined light from star and planet decreases by a measurable amount during the eclipse. By comparing the light received when the planet is visible to when it is hidden, astronomers can isolate the planet's own emission and study its temperature, composition, and atmospheric structure. Some exoplanets have day-side temperatures hot enough to vaporize rock and metal, creating exotic atmospheric compositions including silicon monoxide and iron vapor. The temperature difference between the day and night sides of tidally locked planets can exceed hundreds of degrees, driving powerful winds that redistribute heat around the globe. Thermal phase curves, which track how a planet's brightness changes as it orbits, reveal weather patterns and heat transport on distant worlds. These glowing atmospheres provide windows into conditions that have no analog in our own solar system. Planetary nebulae mark the final breaths of medium-sized stars. When stars between about 1/2 and 8 times the mass of the Sun exhaust their nuclear fuel, they shed their outer layers in expanding shells of gas that form planetary nebulae. These glowing remnants display an astonishing variety of shapes, from simple spherical bubbles to complex hourglasses, spirals, and jet-driven structures. The dying star at the center becomes a hot white dwarf, whose ultraviolet radiation ionizes the expelled gas, causing it to fluoresce in vivid colors that depend on its chemical composition. Despite their name, planetary nebulae have no connection to planets. The term originated when early astronomers thought these round, fuzzy objects resembled planetary disks through their telescopes. The nebula phase lasts only about 20,000 years, a brief moment in cosmic terms, before the gas disperses into the interstellar medium and becomes too diffuse to observe. During this time, the nebula enriches its surroundings with elements like carbon, nitrogen, and oxygen that were synthesized in the star's interior. Our own Sun will produce a planetary nebula approximately 5 billion years from now, briefly illuminating the surrounding space before fading into obscurity as a cooling white dwarf. Supermassive black holes can regulate star formation across entire galaxies. The supermassive black holes at the centers of galaxies do not simply consume matter passively. They actively influence the evolution of their host galaxies through powerful feedback processes. When a black hole accretes matter rapidly, it can launch jets and winds that heat the surrounding gas, preventing it from cooling and collapsing to form new stars. This negative feedback helps explain why the largest galaxies have relatively old stellar populations, despite containing vast reservoirs of potentially star-forming gas. The correlation between black hole mass and the properties of host galaxy bulges suggests that black holes and galaxies co-evolve, each influencing the growth of the other. In some cases, black hole activity may also trigger star formation by compressing gas, as jets plow through the interstellar medium. This delicate balance between suppressing and triggering star formation shapes how galaxies develop over billions of years. Understanding black hole feedback is essential for explaining why galaxies have the sizes and stellar populations we observe today. Some stars orbit the galactic center on paths tilted far above the Milky Way's disk. While most stars in the Milky Way orbit within the thin galactic disk, a population of stars travels on highly inclined orbits that carry them thousands of light-years above and below the galactic plane. These halo stars often have very different properties from disk stars, typically being older, lower in heavy elements, and moving on more elongated and randomly oriented paths. Many halo stars are ancient relics from the galaxy's earliest formation period, before the disk had fully established itself, while others may be the remnants of dwarf galaxies that were accreted and torn apart over billions of years. The Gaia satellite has mapped the motions of over 1 billion stars, revealing streams and structures in the halo that trace the ghosts of consumed companion galaxies. Some of the most metal-poor stars known, containing only trace amounts of elements heavier than hydrogen and helium, are found on these tilted halo orbits. These stellar fossils provide direct evidence about conditions in the universe when the first generations of stars were forming. The galactic halo extends far beyond the visible disk, containing old globular clusters and sparse stellar populations out to distances of hundreds of thousands of light-years. Shock waves from supernovae can trigger new waves of star formation. When a massive star explodes as a supernova, the resulting shock wave races outward at thousands of kilometers per second, compressing any gas clouds it encounters along the way. This compression can push material that was previously too diffuse over the threshold for gravitational collapse, initiating the formation of new stars from gas that might have remained dormant for millions of years. The process represents a cosmic recycling that links stellar death to stellar birth in an ongoing cycle of regeneration. Observations of star-forming regions often reveal evidence of past supernova activity, with bubble-shaped voids surrounded by dense, actively forming stellar populations. Our own solar system may owe its existence to a nearby supernova whose shockwave triggered the collapse of the molecular cloud that became the Sun and planets. Isotopic anomalies in ancient meteorites provide evidence of freshly synthesized radioactive elements that could only have come from a supernova shortly before the solar system formed. This chain of stellar generations connects every star, including our Sun, to the deaths of more massive predecessors. Some binary stars are so close that one pulls material off the surface of the other. Mass-transferring binary systems occur when two stars orbit close enough that one expands to fill its Roche lobe, the gravitational boundary beyond which material is pulled toward the companion star. As gas streams from the donor star, it typically forms an accretion disk around the receiving companion, spiraling inward and releasing gravitational energy as heat and radiation. White dwarfs in such systems can accumulate hydrogen on their surfaces until it reaches sufficient temperature and density to ignite in a thermonuclear runaway, producing a classical nova that can brighten a star system by factors of thousands. If enough mass accumulates, a white dwarf may exceed the Chandrasekhar limit and explode as a Type Ia supernova, one of the most precisely calibrated distance indicators in cosmology. Neutron stars and black holes in mass-transferring binaries create X-ray binary systems, where the accretion disk glows brilliantly in X-ray wavelengths. The transfer of mass and angular momentum in these systems can dramatically alter the evolutionary paths of both stars involved. These interacting binaries serve as cosmic laboratories for studying accretion physics, thermonuclear burning, and the extreme conditions near compact objects. Cosmic dust grains can contain crystalline structures forged in dying stars. The tiny particles of dust drifting through interstellar space often contain crystals of silicates, oxides, and carbon compounds that formed in the outflows of dying stars. As red giant stars shed their outer layers, the cooling gas allows minerals to condense into microscopic solid grains, some with well-ordered crystalline structures and others in amorphous forms. These cosmic dust grains serve as building blocks for new planets, eventually accreting into larger bodies as material collapses to form protoplanetary disks around young stars. Studies of interplanetary dust particles and material from comets have revealed pre-solar grains that predate our solar system, carrying isotopic signatures of the specific stars in which they formed. Some of these ancient grains contain diamond nanocrystals that may have formed in supernova explosions or through shock processes in interstellar space. The crystalline silicates detected in the disks around young stars reveal the thermal processing that occurs during planet formation. Every rocky planet, including Earth, inherited materials that were ultimately forged in stellar furnaces and transported through interstellar space before coalescing into worlds. Stellar nurseries can form intricate networks of filaments filled with newborn suns. Molecular clouds, the birthplaces of stars, often develop complex filamentary structures that channel gas along narrow threads spanning many light years. These cosmic filaments arise from the combined effects of turbulence, magnetic fields, and gravity, creating web-like networks that funnel material toward dense cores where star formation occurs. Observations with the Herschel Space Observatory revealed that filaments are ubiquitous in star-forming regions, with widths that are remarkably uniform at approximately 1/10 of a light-year. Stars tend to form preferentially at the intersections of filaments, where multiple streams of inflowing material converge to create the densest concentrations of gas. The filaments themselves may fragment along their lengths, producing chains of cores that will become individual stars or binary systems. Within regions like the Orion Nebula or the constellation Taurus, intricate networks of these glowing threads crisscross across the sky, visible in infrared light that penetrates the obscuring dust. Understanding how these structures form and evolve is key to understanding the initial conditions for starbirth. Some planets develop thick atmospheres of hydrogen that dwarf their rocky cores. Mini-Neptunes are a class of exoplanet with no analogue in our solar system, featuring relatively small rocky or icy cores surrounded by thick atmospheres of hydrogen and helium that can comprise a significant fraction of their total mass. These worlds are larger than Earth but smaller than Neptune and Saturn, typically 2 to 4 times Earth's diameter, and they appear to be extremely common in the galaxy. The substantial gas envelopes surrounding these planets likely formed early in their histories, when hydrogen and helium from the protoplanetary disk was still available to be captured by forming worlds. Without massive enough cores to attract and retain gas in the manner of true gas giants, mini-Neptunes represent an intermediate outcome of planet formation. Some of these worlds may lose their atmospheres over billions of years due to stellar radiation, potentially transforming into rocky super-Earths. The transition between worlds that retain thick atmospheres and those that shed them defines an important boundary in planetary evolution. Studying the compositions and structures of these puffy planets helps astronomers understand the diversity of outcomes possible during planet formation. The chemical fingerprints in starlight can reveal the composition of distant worlds. When starlight passes through a planet's atmosphere during a transit, specific wavelengths are absorbed by molecules in the atmosphere, creating a distinctive pattern of dark lines in the observed spectrum. This technique, called transmission spectroscopy, allows astronomers to detect the presence of water, sodium, potassium, methane, carbon dioxide, and other compounds in the atmospheres of distant exoplanets. The James Webb Space Telescope has greatly expanded these capabilities, detecting atmospheric signatures in planets dozens of light years away that would have been impossible to analyze with earlier instruments. Similarly, when planets reflect light from their stars or emit their own thermal radiation, emission spectra reveal the conditions and compositions on their day sides. The search for biosignature gases like oxygen, methane, and ozone in exoplanet atmospheres represents one frontier in the quest to find life beyond Earth. Each atmospheric detection builds our understanding of planetary diversity and the conditions that exist on worlds very different from our own. These spectroscopic techniques transform points of light into characterized worlds with known atmospheric properties. Relics of ancient galaxies remain scattered throughout the Milky Way. The Milky Way has grown throughout its history by consuming smaller galaxies, and the remnants of these ancient collisions persist today as streams of stars orbiting on unusual paths. The Gaia satellite has identified numerous stellar streams tracing across the sky, ribbons of stars that were once bound together in dwarf galaxies before being stretched and torn apart by the Milky Way's gravity. Some of the oldest stars in our galaxy may have originated in these absorbed systems, rather than forming within the Milky Way itself. The Sagittarius dwarf galaxy is currently being consumed, its stars forming a great arc that wraps almost completely around our galaxy. Other streams preserve the memory of collisions that occurred billions of years ago, their stars now scattered across the halo and disk. Archaeological studies of these stellar fossils allow astronomers to reconstruct the merger history of our galaxy and understand how it grew to its present size. These remnant structures carry chemical and kinematic signatures that betray their extragalactic origins, despite now being incorporated into the Milky Way. Some stars are surrounded by dusty disks, left over from planet formation. Debris disks are belts of rocky and icy material orbiting mature stars, remnants of the planet formation process that never coalesced into major planets. Unlike the gas-rich protoplanetary disks around young stars, debris disks consist primarily of dust and larger bodies that continue to collide and grind down over time. Our own solar system hosts two prominent debris disks, the asteroid belt between Mars and Jupiter, and the Kuiper belt beyond Neptune. The dust in debris disks is constantly being removed by stellar radiation pressure and Poynting-Robertson drag, meaning it must be continually replenished by collisions between larger parent bodies. Observations of debris disks around other stars have revealed gaps, warps, and asymmetries that suggest the gravitational influence of unseen planets sculpting the material. The star Fomalhaut hosts one of the most famous debris disks, with a sharply defined inner edge that implies a planet herding the dust into place. These systems provide laboratories for studying the late stages of planetary system evolution and the processes that shape asteroids and comets. Intergalactic gas can stretch in narrow filaments that connect distant clusters. The cosmic web is the largest structure in the universe, a network of dark matter and gas filaments that span tens of millions of light-years, connecting the galaxy clusters at their intersections. Along these intergalactic highways, vast quantities of warm and hot gas flow between structures, carrying material that may eventually fall into growing galaxies. The filaments are so diffuse that detecting their gas content directly has proven challenging, though observations of quasars whose light passes through these structures reveal telltale absorption signatures. Computer simulations of cosmic structure formation predict this web-like arrangement, with matter collapsing along filaments toward dense nodes where galaxy clusters reside. The spaces between filaments are nearly empty cosmic voids, the most underdense regions in the universe, where few galaxies are found. Understanding the distribution of matter in the cosmic web helps cosmologists constrain the properties of dark matter and dark energy that govern large-scale structure. The filaments contain perhaps half of all the ordinary matter in the universe, material that has neither fallen into galaxies nor been shocked to the high temperatures found in cluster cores. Some planets orbit dead stars that emit little more than faint ghostly light. White dwarfs, the cooling remnants of sun-like stars, can host planets that survived the violent late stages of stellar evolution, persisting in orbit around these stellar corpses. When a star like the Sun exhausts its nuclear fuel, it expands into a red giant that may engulf inner planets before shedding its outer layers and contracting into a dense white dwarf. Planets orbiting further out may survive this transformation, though their orbits may be destabilized by the changing mass distribution. Observations have revealed debris around white dwarfs that appears to come from rocky bodies being torn apart and accreted, evidence that planetary material persists around these dead stars. A few confirmed planets orbiting white dwarfs demonstrate that worlds can survive stellar death or form anew from the debris. These systems offer a glimpse into the far future of our own solar system, when the Sun has exhausted its nuclear fuel and cooled to a dim white dwarf. Any observers on surviving worlds would witness a sky dominated by a small, faint cinder where once a brilliant sun had shone. The atmospheres of some gas giants glow in infrared wavelengths. Gas giant planets emit more energy than they receive from the Sun, due to interior heat left over from their formation, causing their atmospheres to glow in infrared light invisible to human eyes. Jupiter and Saturn both radiate approximately twice as much energy as they absorb from sunlight, with internal heat driving convection, storms, and atmospheric dynamics. This excess heat stems from the slow gravitational contraction of the planets, which converts gravitational potential energy into thermal energy over billions of years. In the case of Saturn, an additional heat source may come from helium rain, where helium drops settle through the metallic hydrogen interior and release energy as they descend. For hot Jupiters orbiting close to their parent stars, the dayside temperatures become so extreme that the planets glow visibly in the infrared, sometimes hot enough to emit faint visible light. Infrared observations reveal temperature maps of exoplanet atmospheres, showing hotspots, cold regions, and weather patterns. These glowing atmospheres represent nature's own furnaces, radiating the heat of formation and ongoing internal processes. Tidal interactions can twist stellar envelopes into elongated shapes. When two stars orbit each other closely, the gravitational force from each star varies across the diameter of its companion, creating tidal bulges that distort the stars into elongated shapes. In extreme cases of very close binary stars, these tidal distortions can transform spherical stars into egg-shaped or teardrop configurations pointing toward each other. The energy required to maintain these tidal bulges is extracted from the orbital motion, gradually shrinking the orbit over time and potentially leading to eventual merger. Tidal forces also synchronize the rotation of stars to match their orbital periods, so that each star keeps the same face pointing toward its companion. In some binary systems, the tidal distortions are significant enough to affect stellar evolution, altering the internal structure and energy transport within the deformed stars. These same tidal forces operate in planet-moon systems, explaining why the Moon always shows the same face to Earth, and why some close-in exoplanets are expected to be tidally locked. The interplay between tidal forces and orbital dynamics shapes the evolution of countless binary and planetary systems throughout the cosmos. Some galaxies host enormous cavities where past explosions cleared out vast regions of gas. Active galactic nuclei and multiple supernova explosions can carve out enormous bubbles in the hot gas that permeates galaxy clusters, creating X-ray visible cavities spanning hundreds of thousands of light-years. These cavities form when jets from supermassive black holes plow through the surrounding medium, pushing aside the hot intracluster gas and inflating radio-emitting lobes. The energy required to excavate these bubbles is staggering, equivalent to the total energy output of billions of supernovae, sustained over millions of years. The displaced gas creates cooler regions that contrast with the surrounding hot medium, revealing the bubble's extent in X-ray observations. In the Perseus cluster, multiple pairs of cavities at different distances from the central galaxy record distinct episodes of black hole activity over the past several hundred million years. These cavities represent a crucial mechanism by which black holes deposit energy into their environments, regulating the cooling of gas and the formation of new stars. Without this energetic feedback, far more gas would cool and collapse, leading to unrealistically high rates of star formation in the largest galaxies. Interstellar clouds can freeze molecules onto dust grains in icy layers. In the coldest, densest regions of molecular clouds, temperatures can drop to only 10 degrees above absolute zero, cold enough for common gases to freeze onto the surfaces of dust grains in layers of ice. These icy mantles contain water, carbon monoxide, carbon dioxide, ammonia, methanol, and more complex organic molecules that stick to the grain surfaces and remain frozen until the region warms. When stars begin to form and heat their surroundings, these ices evaporate and release their molecular cargo into the gas phase, where they can participate in chemistry that produces ever more complex organic species. Comets, which formed in the cold outer regions of the early solar system, preserve some of these primordial ices and deliver them to planets during impacts. The organic molecules found in meteorites and cometary material have been linked to these interstellar ice processes, suggesting that some building blocks of life were delivered to early Earth from space. Laboratory simulations have shown that ultraviolet radiation can process these ices into amino acids and other biologically relevant compounds. The frozen molecular layers on interstellar dust thus represent an important reservoir of prebiotic chemistry. Stellar mass black holes can form when massive stars collapse. When stars more than about 20 times the mass of the Sun exhaust their nuclear fuel, the core collapse that ensues can be so violent that no force is able to halt the implosion, resulting in the formation of a stellar mass black hole. These collapsed remnants typically have masses between a few and several tens of times the Sun's mass, significantly smaller than the supermassive black holes at galaxy centers, but form through an entirely different mechanism. The formation event may produce a supernova that blows off the outer layers while the core collapses, or in some cases, the star may collapse directly without a visible explosion. Stellar mass black holes in binary systems can be detected when they accrete material from companion stars, heating the infalling gas and emitting X-rays detectable by space telescopes. The LIGO and Virgo gravitational wave observatories have detected dozens of stellar mass black hole mergers, revealing a population of these objects throughout the universe. Some of these mergers involve black holes more massive than expected from standard stellar evolution, hinting at alternative formation channels. Each stellar mass black hole represents the compressed remains of what was once a luminous massive star. The surfaces of neutron stars contain matter packed at astonishing densities. Neutron stars are the ultra-dense remnants of massive stars that have undergone supernova explosions, compressing a mass greater than the Sun's into a sphere only about 20 kilometers across. At these densities, matter is squeezed so tightly that electrons and protons merge into neutrons, creating a material composed almost entirely of neutrons packed as closely as the strong nuclear force permits. A teaspoon of neutron star material would weigh approximately 6 billion tons, more than the combined weight of all humans on Earth. The surface gravity on a neutron star is about 200 billion times stronger than Earth's, strong enough that any mountains would be measured in millimeters rather than meters. Beneath the crystalline crust lies a superfluid interior, where neutrons flow without friction, and protons form a superconducting liquid. The cores of the most massive neutron stars may contain exotic forms of matter, including hyperons, kaon condensates, or even quark matter in a strange quark-gluon plasma. These extreme environments provide natural laboratories for studying matter under conditions impossible to replicate on Earth. Some exoplanets orbit in chaotic systems where gravitational pulls constantly shift their paths. Not all planetary systems settle into stable, predictable configurations. Some contain multiple planets whose mutual gravitational interactions produce chaotic, constantly evolving orbits. In these systems, the orbital parameters can change dramatically over millions of years, with eccentricities, inclinations, and even orbital distances shifting as planets exchange angular momentum. Close approaches between planets can transfer energy in ways that are extremely sensitive to initial conditions, making long-term predictions impossible beyond certain horizons. Some systems may eventually eject planets entirely or send them crashing into their stars after extended periods of gravitational jostling. The presence of multiple giant planets, especially on crossing or nearly crossing orbits, increases the likelihood of chaotic dynamics. Our own solar system is technically chaotic over timescales of millions of years, though the effects are mild, and the planets will likely remain in orbit for billions of years to come. Studying chaotic planetary systems helps astronomers understand the stability boundaries that determine which configurations can persist over stellar lifetimes. Jets from young stars can carve long channels through surrounding gas. As young stars form and accrete material from their surrounding disks, they often launch bipolar jets of gas that shoot outward at hundreds of kilometers per second along their rotation axes. These jets plow through the surrounding molecular cloud, clearing tunnels and creating shock waves, where the fast-moving jet material collides with the slower ambient gas. Herbig Haro objects are the glowing knots and bow shocks produced at these collision fronts, visible as bright nebulae that move noticeably over timescales of years to decades. The jets can extend for several light-years, far beyond the protoplanetary disks from which they originate, carrying away angular momentum that allows accretion onto the star to continue. The mechanism that launches these jets involves the interaction of magnetic fields with the rotating disk, though the detailed physics remains an active area of research. As the young star matures and clears its surrounding envelope, the jet activity typically diminishes and eventually ceases. These outflows represent a crucial phase in star formation, affecting both the forming star and its surrounding environment. Ultra-faint dwarf galaxies contain few stars, yet significant dark matter. Ultra-faint dwarf galaxies are the smallest and dimmest galaxies known, containing only a few thousand stars spread across regions several hundred light-years in diameter. Despite their meager stellar content, these galaxies appear to be dominated by dark matter to an even greater extent than larger galaxies, with mass-to-light ratios hundreds of times higher than the Sun's. The stars within these systems move faster than expected, based on the visible mass alone, indicating the presence of substantial unseen matter holding the galaxy together gravitationally. Many ultra-faint dwarfs have been discovered orbiting the Milky Way since systematic searches began, nearly doubling the known population of satellite galaxies around our home. These dim systems represent the faint end of the galaxy luminosity function, and may be fossils from the early universe, relatively unchanged since their formation billions of years ago. Their high dark matter content makes them prime targets for indirect dark matter detection experiments, searching for signals from particle annihilation or decay. Understanding ultra-faint dwarfs helps astronomers constrain models of dark matter and galaxy formation at the smallest scales. Star formation can stall when intense radiation evaporates surrounding gas. When massive stars form within molecular clouds, their intense ultraviolet radiation begins to ionize and heat the surrounding gas, driving it away and potentially preventing additional stars from forming nearby. This negative feedback limits the efficiency of star formation in many giant molecular clouds, explaining why only a small percentage of available gas is typically converted into stars before the cloud disperses. The expanding regions of ionized gas, called H2 regions, create bubble-like structures that can be seen throughout star-forming areas of the Milky Way and other galaxies. Eventually, the combined radiation and stellar winds from multiple massive stars can completely disrupt their birth cloud, exposing the newborn cluster to open space. The remaining gas is driven into denser shells at the edges of the expanding bubble, where it may trigger secondary waves of star formation. This interplay between star formation and its own disruptive feedback shapes the structure and evolution of star-forming regions throughout the universe. The result is self-regulating star formation that rarely converts more than a few % of molecular cloud mass into stars. Some planets contain seas of liquid hydrocarbons instead of water. Titan, Saturn's largest moon, hosts lakes and seas of liquid methane and ethane on its surface, making it the only world besides Earth known to have stable bodies of liquid at its surface. The surface temperature on Titan, approximately -179 degrees Celsius, is cold enough that hydrocarbons, which are gases on Earth, exist as liquids and play the role that water plays in Earth's hydrological cycle. Methane rain falls from Titan's thick atmosphere, carving river channels and collecting in lakes that have been mapped by the Cassini spacecraft's radar instruments. The largest of these bodies, Kraken Mare, covers an area larger than Earth's Caspian Sea and reaches depths of hundreds of meters. Waves may ripple across these alien seas, driven by Titan's gentle winds, though direct observation of such waves remains challenging. The presence of complex organic chemistry in Titan's atmosphere and surface makes this moon one of the most intriguing targets in the search for prebiotic chemistry or alternative forms of life. NASA's Dragonfly mission, planned for launch in the coming years, will explore Titan's surface with a drone-like rotorcraft. Gamma-ray bursts can unleash colossal amounts of energy in a single moment. Gamma-ray bursts are the most energetic explosions in the universe since the Big Bang, releasing in seconds the energy that the Sun will produce over its entire 10 billion-year lifetime. These cosmic flashbulbs were first detected by military satellites in the late 1960s and initially defied explanation due to their extreme brightness and random distribution across the sky. We now recognize two main classes: short bursts lasting less than 2 seconds, caused by merging neutron stars, and long bursts lasting tens of seconds or more, associated with the core collapse of extremely massive stars. The gamma-ray emission is produced when ultra-relativistic jets punch through collapsing stellar envelopes or merger debris, accelerating particles to tremendous energies. If a gamma-ray burst occurred within a few thousand light-years of Earth, and its jet pointed at us, the radiation could pose a significant threat to life. However, such events are extremely rare in galaxies like the Milky Way, and no mass extinction has been conclusively linked to a nearby gamma-ray burst. These powerful explosions serve as beacons visible across most of the observable universe, probing conditions at extreme distances. Some asteroid families share a common origin in ancient collisions. Asteroid families are groups of asteroids that share similar orbital elements and compositions, because they all originated from the destruction of a single larger parent body in an ancient collision. When a large impact shatters an asteroid, the fragments disperse, but continue to orbit the Sun on similar paths, gradually spreading out over millions of years while retaining their common characteristics. The Coronis, Eos, and Themis families are well-known examples in the main asteroid belt, each containing hundreds of members that can be traced back to their original progenitor. By studying the composition and orbits of family members, astronomers can reconstruct the size and structure of the original body and the energy of the collision that destroyed it. Young families whose members have not yet dispersed widely reveal the immediate aftermath of asteroid disruption, while older families show how orbital dynamics gradually mix and spread the debris. Some asteroid families have been linked to specific dust bands in the solar system, the fine particles still tracing the paths of their ancient collisions. Understanding asteroid families helps us piece together the violent collisional history of the asteroid belt. Planetary magnetic fields can trap charged particles in giant glowing belts. Planets with strong magnetic fields, like Earth and Jupiter, can capture charged particles from the solar wind and trap them in toroidal regions called radiation belts or Van Allen belts. These energetic particles spiral along magnetic field lines, bouncing back and forth between the magnetic poles and slowly drifting around the planet. The belts can contain protons and electrons with energies high enough to damage spacecraft electronics and pose radiation hazards to astronauts. Jupiter's radiation belts are the most intense in the solar system, powered by particles from the solar wind and volcanic material ejected by the Moon Io. When particles precipitate into the polar atmosphere along field lines, they collide with atmospheric molecules and produce the glowing auroras visible at high latitudes. Earth's Van Allen belts were among the first major discoveries of the space age, detected by Geiger counters aboard the Explorer satellites in 1958. The dynamics of radiation belts vary with solar activity, intensifying during geomagnetic storms when bursts of solar wind particles inject fresh energy into the system. Relativistic effects near black holes can distort the passage of time. General relativity predicts that time passes more slowly in stronger gravitational fields, an effect called gravitational time dilation that becomes extreme near the event horizons of black holes. An observer falling toward a black hole would perceive their own time passing normally, while an outside observer would see their clock slow dramatically and eventually appear to freeze at the event horizon. Near a spinning black hole, frame dragging adds additional complexity, as the rotation of spacetime itself carries everything within the ergosphere along with it. These relativistic effects have been confirmed through precision measurements with atomic clocks at different altitudes on Earth, and through observations of stars orbiting close to the supermassive black hole at our galaxy's center. The stars orbiting Sagittarius A star move at significant fractions of the speed of light at closest approach, requiring relativistic corrections to accurately predict their motions. Material in accretion disks close to black holes experiences significant time dilation, affecting how we interpret the light and spectra we observe from these regions. Such extreme conditions provide natural laboratories for testing general relativity in the strong field regime. Some galaxies rotate around invisible concentrations of dark matter. The existence of dark matter was first inferred from observations that galaxies rotate faster than expected based on their visible mass alone, implying the presence of unseen matter, providing additional gravity. Galaxy rotation curves, which plot how fast stars orbit at different distances from the galactic center, typically remain flat, far beyond where visible matter drops off, indicating massive dark matter halos extending well beyond the stellar disk. Dwarf spheroidal galaxies exhibit some of the highest dark matter to visible matter ratios known, with their stars moving far too fast to be bound by visible matter alone. Computer simulations of cosmic structure formation that include dark matter successfully reproduce the observed distribution of galaxies, suggesting that dark matter acts as scaffolding around which visible matter collects. Despite decades of searching, the particle nature of dark matter remains unknown, with candidates ranging from weakly interacting massive particles to ultralight axions. Direct detection experiments deep underground aim to catch the rare interactions if dark matter particles collide with ordinary atoms. The dark matter halos surrounding galaxies represent the dominant mass component of most systems, outweighing stars and gas by factors of 5 to 10. The atmospheres of some exoplanets contain clouds made of vaporized minerals. On the hottest exoplanets, temperatures can exceed 2000 degrees, hot enough to vaporize rock and create clouds of condensed silicates, iron droplets, or other refractory materials. These exotic clouds form when mineral vapors rise from the blazing day side, cool at higher altitudes, and condense into droplets that rain back down toward the surface in an endless cycle. Observations with the Hubble and James Webb Space Telescopes have detected signatures consistent with such mineral clouds in the atmospheres of several ultra-hot Jupiters. The cloud composition depends on temperature, with different minerals condensing at different altitudes and creating layered cloud decks similar in structure, though not composition, to the water clouds of Earth. On some worlds, the clouds may include exotic species like corundum, the mineral that forms rubies and sapphires, or titanium oxide compounds. These alien weather patterns challenge our understanding of atmospheric chemistry and dynamics, as they involve materials we normally consider solid on Earth. The reflectivity and opacity of mineral clouds affect how much heat these planets radiate back to space, shaping their overall energy budgets. Starquakes can rattle the surfaces of neutron stars. Neutron star crusts, though incredibly dense, are solid crystalline layers that can accumulate stress over time, and occasionally fracture in events called starquakes. These crustal failures release tremendous amounts of energy, sometimes producing observable bursts of X-rays or gamma rays that astronomers can detect across interstellar distances. The intense magnetic fields of magnetars can exert enough force on the crust to trigger especially violent starquakes, producing flares that briefly outshine entire galaxies in gamma-ray luminosity. During a starquake, the neutron star may slightly change shape, and the resulting redistribution of mass can alter its rotation rate in a phenomenon called a glitch. Pulsar glitches, sudden small increases in the rotational frequency, have been observed in many neutron stars and are thought to result from crustal fractures, or the sudden transfer of angular momentum from a faster spinning superfluid interior. The 2004 giant flare from the magnetar SGR 1806-20 released more energy in 1/10 of a second than the Sun emits in 100,000 years. Starquakes provide unique windows into the extreme physics of neutron star crusts, testing our understanding of matter at nuclear densities. Some stars are so massive that they fuse elements up to iron in their cores. The most massive stars in the universe progress through a sequence of nuclear burning stages, fusing successively heavier elements from hydrogen through helium, carbon, oxygen, silicon, and finally iron. Each stage releases less energy than the last and proceeds more rapidly, with the final silicon burning phase lasting only days before the core fills with iron group elements. Iron is special because fusing it absorbs energy rather than releasing it, making iron the end of the line for energy-generating nuclear fusion in stellar cores. When a massive star's core becomes composed primarily of iron, it can no longer support itself against gravity and collapses catastrophically, triggering a supernova explosion. During the brief supernova itself, the extreme temperatures and neutron fluxes allow the rapid neutron capture process to build elements heavier than iron, including gold, platinum, and uranium. These heavy elements are dispersed by the explosion and eventually incorporated into new stars, planets, and perhaps even life forms. The layered onion-like structure of a massive star just before core collapse contains zones of different composition, each representing a successive burning stage. Distant planetary systems can contain icy bodies far beyond their giant planets. Beyond Neptune, our solar system hosts the Kuiper Belt, a vast region populated by millions of icy objects that represent debris left over from planet formation. Pluto, Eris, and other dwarf planets reside in this distant zone, along with countless smaller bodies composed primarily of frozen water, methane, ammonia, and other volatiles. Observations of debris disks around other stars suggest that such outer belts of icy material are common features of planetary systems, extending to hundreds of astronomical units from their central stars. These distant reservoirs may occasionally send objects toward the inner system through gravitational perturbations, creating comets that carry ancient ice and organics to warmer regions where they can be studied. The proposed Oort cloud surrounds our solar system at even greater distances, a vast shell of icy bodies extending perhaps halfway to the nearest stars. Studying the outer reaches of planetary systems helps astronomers understand the original distribution of material in protoplanetary disks, and how planetary migration may have scattered objects outward. These frozen frontiers represent some of the most pristine material in our solar system, preserving conditions from 4.5 billion years ago. The faint glow between galaxies contains the afterglow of ancient stars. Intergalactic space, though seemingly empty, contains a diffuse glow called the intracluster light, or intracluster stellar component, produced by stars that have been stripped from their parent galaxies and now wander freely through cluster environments. These orphaned stars were pulled from their home galaxies by tidal forces during gravitational interactions, and now contribute a faint but measurable luminosity spread throughout galaxy clusters. The intracluster light can amount to 10 to 50% of a cluster's total stellar luminosity, representing billions of stars no longer bound to any individual galaxy. Observations in the outskirts of galaxy clusters have revealed streams, shells, and plumes of this diffuse light, tracing the dynamical history of past galaxy encounters. The color and brightness of the intergalactic glow provides information about the stellar populations involved, typically showing older, redder stars consistent with material stripped from galaxy outskirts. Deep images from the Hubble Space Telescope and ground-based observatories have revealed this ghostly luminescence surrounding nearby galaxy clusters. This scattered starlight is a testament to the violent interactions that reshape galaxies as they fall together in the densest cosmic environments. Some comets release jets of dust and gas as they approach their stars. As comets approach the inner solar system and warm under the sun's radiation, subsurface ices begin to sublimate and burst through the crust in focused jets of gas and dust. These jets can propel material away from the nucleus at speeds of hundreds of meters per second, creating the characteristic fuzzy coma that surrounds active comets. The Rosetta mission's detailed observations of Comet 67P revealed numerous jets emanating from fissures and pits on the comet's surface, their activity varying with the comet's rotation and proximity to the Sun. As the gas flows away from the nucleus, it drags along dust particles that scatter sunlight and form the distinctive tail that stretches away from the Sun. Cometary jets are not steady. They can turn on and off as different regions of the surface rotate into and out of sunlight, creating time-varying patterns of activity. The reaction force from these jets can also subtly alter the comet's orbit over time through a mechanism called outgassing-induced non-gravitational acceleration. Studying cometary jets reveals the composition of these primitive solar system bodies and provides insights into the materials available when our planetary system was young. Galactic winds can blow gas out of galaxies and quench star formation. When intense bursts of star formation or active galactic nuclei release enormous amounts of energy, they can drive powerful outflows that expel gas from galaxies at speeds of hundreds or even thousands of kilometers per second. These galactic winds carry away the raw material needed to form stars, potentially shutting down star formation entirely and leaving the galaxy red and dead. The winds are often visible in observations as expanding shells and filaments of gas extending far beyond the galaxy's disk, out into the circumgalactic medium. Starburst galaxies, which are forming stars at rates far above normal, frequently show evidence of strong outflows driven by the combined effect of supernovae and stellar winds from massive stars. In galaxies with active supermassive black holes, the jets and radiation from the accretion process can drive even more powerful winds that affect the entire galaxy. The expelled gas may eventually fall back onto the galaxy or remain in the halo, where it could fuel future star formation. Understanding galactic winds is crucial for explaining why galaxies stop forming stars and why the relationship between galaxy mass and star formation efficiency changes over cosmic time. Some stars wander the galaxy at high speeds after gravitational encounters. Runaway stars are high-velocity objects hurtling through the galaxy at speeds far exceeding those of their neighbors, ejected from their birthplaces by close gravitational encounters or supernova explosions. When massive stars in tight binary or multiple systems interact gravitationally, energy can be exchanged in ways that accelerate one star to high velocity, while its companion is captured or slowed. Another mechanism occurs when a binary companion explodes as a supernova. The surviving star may be kicked into a high-velocity trajectory by the sudden loss of gravitational binding. Some runaway stars can be traced back to their origin clusters by rewinding their motion, revealing their ejection point and sometimes even identifying the system that expelled them. Blue stragglers and other anomalous stars in the galactic field may have originated as runaway objects from distant clusters. The bow shocks formed by fast-moving stars plowing through interstellar gas can sometimes be observed in infrared light, marking their rapid passage. These stellar speedsters are gradually dispersing throughout the galaxy, their high velocities reflecting violent events in their distant pasts. The surfaces of some exoplanets may be covered in oceans of molten rock. Lava-world exoplanets orbit so close to their stars that their surfaces are heated to temperatures exceeding 1500 degrees, hot enough to melt rock and create global oceans of magma. These extreme worlds experience radiation so intense that rock vaporizes from their surfaces, creating thin atmospheres of silicon, iron, and other refractory elements. The planet 55 Cancri E, approximately twice Earth's diameter, shows evidence of extreme surface temperatures on its day side, possibly indicating an active lava surface continuously refreshed by volcanism. Unlike any world in our solar system, these lava planets represent an exotic outcome of planetary formation, where rocky bodies end up in tight, scorching orbits. The boundary between solid and liquid rock shifts across the surface depending on local illumination, creating dynamic landscapes that may change dramatically as the planet rotates. Some of these worlds may be tidally locked, with permanent hemispheres of molten and solid rock facing and away from their stars respectively. Studying lava planets helps scientists understand the extremes of rocky planet evolution and the behavior of silicate materials under conditions impossible to reproduce on Earth. Supernova remnants can contain swirling knots of highly enriched gas. The debris from supernova explosions expands outward, carrying freshly synthesized heavy elements from the exploded star's core, and this material often forms complex structures, including dense knots, filaments, and fast-moving bullets. These clumps of enriched gas can contain elements like oxygen, silicon, sulfur, and iron, in abundances far exceeding the surrounding interstellar medium, representing the concentrated ashes of nuclear burning in the progenitor star. The Cassiopeia A supernova remnant displays spectacular knots of debris moving at thousands of kilometers per second, their composition revealing the layered structure of the star that exploded approximately 350 years ago. These dense clumps are eventually mixed into the interstellar medium, enriching it with the building blocks for rocky planets and the elements necessary for life. The different expansion velocities and compositions of various knots trace back to different layers of the exploded star, providing forensic evidence about the explosion mechanism. Shockwaves passing through these knots produce bright optical and X-ray emission, making them stand out against the more diffuse remnant background. Studying these structures helps astronomers understand how supernovae distribute heavy elements throughout the galaxy. Some galaxies harbor enormous amounts of cold molecular hydrogen. Molecular hydrogen, the primary ingredient for star formation, is difficult to observe directly because it lacks strong emission features at typical interstellar temperatures. Instead, astronomers trace molecular gas through emission from carbon monoxide and other molecules that exist alongside molecular hydrogen in cold, dense clouds. Surveys have revealed that some galaxies, particularly gas-rich spirals and star-bursting systems, contain vast reservoirs of molecular gas that can fuel star formation for billions of years. The Milky Way contains several billion solar masses of molecular gas, concentrated primarily in the spiral arms and the molecular ring near the galactic center. In more extreme systems, molecular gas masses can reach tens of billions of solar masses, dwarfing the gas content of our galaxy. The distribution and kinematics of molecular gas reveal the structure of galaxies and the processes that concentrate gas into star-forming regions. Understanding the molecular gas content of galaxies across cosmic time is essential for reconstructing the history of star formation in the universe. Stellar collisions can create unusually massive and luminous stars. In the dense cores of globular clusters, where stellar densities can reach millions of stars per cubic parsec, physical collisions between stars become possible over the cluster's multi-billion-year lifetime. When two stars merge, the resulting object can be significantly more massive and luminous than either progenitor, temporarily appearing as a rejuvenated star that seems too young for its environment. Blue stragglers are the most common products of such merger events, main sequence stars that appear bluer and more luminous than they should be given the age of their host clusters. These objects stand out dramatically in color magnitude diagrams, lying above the main sequence turnoff, where other cluster stars of similar mass have already evolved away. Some mergers may occur through direct collisions, while others result from the coalescence of close binary systems whose orbits tightened through dynamical interactions. The merger process itself can be violent, with material being ejected and the remnant star exhibiting unusual properties as it settles into a new equilibrium. Stellar collisions demonstrate that stars are not always isolated objects evolving in solitude, but can dramatically alter each other through direct contact. Some planets experience extreme temperature swings between day and night. Planets with thin atmospheres or in tidally locked configurations can exhibit enormous temperature differences between their sunlit and dark hemispheres, creating thermal gradients of hundreds of degrees. The Moon, with essentially no atmosphere, experiences surface temperatures that range from about 120 degrees Celsius in direct sunlight to minus 170 degrees Celsius in shadow. Mercury, despite being closer to the Sun, shows similarly extreme variations due to its tenuous exosphere and slow rotation. For tidally locked exoplanets, the permanent day side can be scorching, while the permanent night side may be frozen, with extreme weather patterns driven by the temperature contrast between hemispheres. Some hot Jupiter exoplanets show day-night temperature differences exceeding 1000 degrees, driving supersonic winds that attempt to redistribute heat from day to night. The efficiency of this heat redistribution determines whether the night side remains habitable or freezes into a permanent ice sheet. These thermal extremes challenge our understanding of atmospheric dynamics and habitability, revealing the delicate balance of factors that determine planetary climate. The outer edges of some galaxies contain stars that barely orbit at escape speed. In the outermost reaches of galaxies, stars orbit so slowly and so far from the center that they are only weakly bound to their host systems. These outer halo stars trace the edge of the galaxy's gravitational influence, where the boundary between bound and unbound becomes increasingly fuzzy. Small perturbations from passing satellite galaxies or tidal interactions with neighbors could easily kick these marginal members free of their host galaxy entirely. Observations of stellar velocities in galaxy outskirts have revealed populations moving at nearly the local escape velocity, suggesting they were recently captured or are on the verge of escaping. The Milky Way's halo extends to hundreds of thousands of light-years from the galactic center, with the most distant known stars orbiting at tremendous distances and orbital periods measured in billions of years. These outer populations often have different chemical compositions and kinematics from disk stars, reflecting their origins in accreted dwarf galaxies rather than in situ formation. Mapping these peripheral stars helps astronomers constrain the total mass and dark matter halo extent of galaxies. Some black holes emit soft X-rays as matter spirals inward. When black holes actively accrete material from companion stars or surrounding gas, the infalling matter forms a superheated accretion disk that emits copious radiation, particularly in X-ray wavelengths. Stellar mass black holes in binary systems can produce X-ray emission bright enough to be detected across the galaxy, making them some of the most luminous X-ray sources in the sky. The temperature of the inner accretion disk, which can reach millions of degrees, determines whether the emission peaks at soft X-ray energies or harder, more penetrating wavelengths. Soft X-ray emission indicates a disk that is relatively cool compared to more energetic systems, often seen in black holes accreting at high rates relative to their maximum. The spectral shape and variability of X-ray emission reveal details about the accretion geometry, the inner disk radius, and sometimes even the spin of the black hole itself. Time variability on scales from milliseconds to months tracks fluctuations in the accretion rate and changing conditions in the disk. X-ray observations have been fundamental to discovering and characterizing black holes throughout our galaxy and in the centers of distant active galaxies. Complex organic molecules can form in cold, dark nebulae. The frigid interiors of molecular clouds, shielded from the ultraviolet radiation that would destroy delicate molecules, host surprisingly complex organic chemistry. Radio astronomers have detected over 200 different molecular species in interstellar space, including alcohols, sugars, ethers, and even amino acid precursors. These molecules form through both gas phase reactions and surface chemistry on dust grains, where atoms stick and combine in ways impossible in the diffuse interstellar medium. The detection of glycine, the simplest amino acid, remains controversial, but other prebiotic molecules like formamide exist in abundance in star-forming regions. When these molecular clouds collapse to form stars and planets, the organic inventory they contain becomes incorporated into the new system, potentially delivering chemical building blocks to young worlds. Comets and meteorites that formed in the cold outer regions of our own solar system carry these interstellar organics, some of which may have survived delivery to early Earth. The complexity of interstellar chemistry suggests that the raw materials for life may be common throughout the cosmos, requiring only appropriate conditions to develop further. Some exoplanet atmospheres expand into huge puffy envelopes. Certain exoplanets, particularly those receiving intense stellar radiation, can have atmospheres so extended that they fill a significant fraction of their Roche lobes, giving them densities lower than styrofoam. These puffy planets, with radii far larger than expected given their masses, present a puzzle for planetary science, because their low densities suggest thick hydrogen-helium envelopes that should have contracted rather than remained expanded. The intense heating from nearby stars may inflate these atmospheres by depositing energy in the deep atmospheric layers, preventing the cooling and contraction that would otherwise occur. Some of the most inflated planets have density lower than Saturn, the least dense planet in our solar system, despite being bombarded by far more radiation. Observations of these extended atmospheres during transits reveal that they are actively losing mass as stellar radiation strips hydrogen from their outer layers. The rate of atmospheric escape can be substantial, with some planets losing millions of tons of atmospheric gas per second in comet-like tails. Understanding why some planets are so inflated while others remain compact helps astronomers constrain models of planetary interiors and atmospheric physics. The earliest galaxies formed when the universe was still young and chaotic. Observations with the James Webb Space Telescope have revealed galaxies that formed within the first few 100 million years after the Big Bang, when the universe was a small fraction of its current age. These early galaxies look very different from the elegant spirals and ellipticals we see nearby, often appearing as irregular clumps of intense star formation lacking the smooth structures that develop later. The conditions in the early universe were more extreme, with denser gas, higher merger rates, and primordial chemical compositions containing almost no elements heavier than helium. Star formation in these proto-galaxies was likely more vigorous and chaotic than in the present-day universe, with massive stars forming, burning, and exploding rapidly to begin enriching the cosmos with heavy elements. Some of the earliest galaxies discovered appear surprisingly massive and structured, challenging models that predicted more gradual assembly over longer timescales. The first billion years of cosmic history represents a crucial epoch when the building blocks of present-day galaxies were being assembled through violent mergers and extreme star formation. Studying these early systems is like cosmic archaeology, revealing the origins of structures as grand as our own Milky Way. Some stars form in metal-poor environments that challenge current models. In the early universe, and in certain present-day environments, stars form from gas containing few heavy elements, conditions quite different from the metal-enriched clouds where the sun was born. The absence of cooling agents like carbon and oxygen, which help gas radiate away energy and collapse more efficiently, changes the physics of star formation and may favor the birth of more massive stars. Observations of ancient stars in the Milky Way's halo, which formed from nearly pristine gas over 10 billion years ago, reveal extremely low metal abundances that reflect the composition of the early cosmos. Despite theoretical predictions that the first stars were exclusively supermassive, we find surviving low-mass metal-poor stars that must have formed under these challenging conditions. Dwarf galaxies in the local group continue to form stars from relatively metal-poor gas, providing nearby laboratories for studying these processes. The transition from population 3 stars, the hypothetical first generation with 0 heavy elements, to population 2 and population 1 stars, traces the chemical enrichment history of the universe. Understanding star formation across the full range of metallicity is essential for reconstructing cosmic history. Galactic bars can funnel gas towards central star-forming regions. Many spiral galaxies, including our own Milky Way, host elongated bar structures at their centers that profoundly influence gas dynamics and star formation. These stellar bars rotate as rigid bodies and create gravitational torques that channel gas from the disk into the central regions, fueling bursts of star formation and potentially feeding central black holes. The streaming motions induced by the bar can concentrate gas into ring-like structures at specific resonant radii, creating zones of enhanced star formation visible in many barred galaxies. About 2/3 of all disk galaxies show evidence of bars, making this a dominant mode of internal secular evolution. The formation of bars may be triggered by instabilities in the disk, or by tidal interactions with companion galaxies. Over cosmic time, bars can dissolve and reform, with their strength and pattern speed evolving as the galaxy's mass distribution changes. The presence of a bar, therefore, reflects both the current dynamical state of a galaxy and its gravitational history. Some planets orbit multiple stars in wide looping trajectories. Circumbinary planets orbit around both stars in a binary system, tracing paths through the complex gravitational field created by two stellar bodies. The discovery of planets like Kepler-16b revealed that these Tatooine-like worlds are not just science fiction, but real outcomes of planet formation in binary environments. These planets face unique challenges during formation, as the gravitational perturbations from two stars can disrupt the protoplanetary disk and destabilize nascent planetesimals. Yet studies have shown that the zone where stable orbits can exist extends surprisingly close to the binary pair, allowing habitable zone planets around some configurations. The orbital dynamics of circumbinary planets are complex, with the paths subtly shifting as the central stars orbit each other and the combined gravitational field evolves. Some circumbinary planets have been found in multi-planet systems, demonstrating that complete planetary systems can develop around binary stars. These exotic worlds expand our understanding of planetary system architectures and the resilience of planet formation under challenging conditions. Cosmic shock fronts can energize particles to extreme velocities. Throughout the universe, shock waves accelerate charged particles to tremendous energies through a process called diffusive shock acceleration. At supernova remnants, particles bounce back and forth across the shock front, gaining energy with each crossing until they reach velocities approaching the speed of light. These cosmic ray particles eventually escape into the interstellar medium, where they rain down on Earth after journeying for millions of years through the galaxy. Similar processes operate at larger scales, where cluster mergers and black hole jets create shocks that accelerate particles in the intergalactic medium. The most energetic cosmic rays carry as much energy as a tennis ball moving at highway speeds, all concentrated in a single subatomic particle. Their origins remain partially mysterious, as such extreme energies require acceleration sites more powerful than ordinary supernova remnants. Radio observations of synchrotron emission, produced when these relativistic particles spiral in magnetic fields, trace the locations of cosmic accelerators throughout the universe. Understanding cosmic ray acceleration connects particle physics to astrophysics across vast scales of energy and distance. Some galaxies shine brightly in radio wavelengths due to energetic processes. Radio galaxies emit enormous amounts of energy at radio wavelengths, typically powered by relativistic jets launched from supermassive black holes at their centers. These jets extend far beyond the visible galaxy, inflating enormous lobes of radio-emitting plasma that can span millions of light-years. The synchrotron radiation produced by electrons spiraling in magnetic fields creates the characteristic radio emission that gives these objects their name. Some of the largest structures in the universe are the extended lobes of giant radio galaxies, dwarfing the optical galaxies at their centers. The power required to maintain these jets over millions of years comes from the gravitational energy released as matter falls toward the central black hole. Radio galaxies are often found at the centers of galaxy clusters, where their jets interact with the hot intergalactic medium and carve out enormous cavities. These were among the first objects discovered when radio astronomy emerged in the mid-20th century, revealing a violent universe invisible to optical telescopes. Dusty tori around active galactic nuclei obscure their central engines. The unified model of active galactic nuclei proposes that the different observed types of active galaxies are actually the same phenomenon viewed from different angles, with dusty torus-shaped structures blocking our view of the central engine in some cases. When we look down the axis of the torus, we see directly into the nucleus and observe bright, broad emission lines from rapidly moving gas close to the black hole. When the torus is viewed edge-on, the dust blocks our direct view of the inner regions, and we observe only narrow emission lines from more distant gas. This simple geometric explanation links quasars, Seyfert galaxies, and other active galaxy types into a coherent picture where viewing angle determines observed properties. Infrared observations have confirmed the presence of warm dust arranged in torus-like configurations around many active nuclei. The dusty torus both hides the central engine and reprocesses its radiation, absorbing ultraviolet and optical light and re-emitting it at longer infrared wavelengths. Understanding this obscuring structure has been essential for constructing a complete census of black hole activity across cosmic history. Some planets may host subsurface lakes, trapped between layers of rock and ice. Beneath the icy surfaces of some moons in the outer solar system, liquid water may not only exist in global oceans, but also in isolated lakes, sandwiched between layers of ice at different depths. Europa's ice shell may be tens of kilometers thick, with pockets of liquid water embedded within this frozen crust, in addition to the vast ocean believed to exist beneath. Similar structures might exist on Ganymede and Callisto, where liquid layers could be trapped between high-pressure ice phases at different depths. On Mars, radar observations have suggested the possible existence of subsurface lakes or briny aquifers beneath the southern polar ice cap, though this interpretation remains debated. These trapped water bodies would be isolated from both the surface and any underlying oceans, creating unique environments with their own chemistry and potential for hosting microbial life. The pressure and temperature at various depths determine where liquid water can exist, creating a complex layered structure in worlds with thick, icy crusts. Future missions carrying ice-penetrating radar and eventually drilling technology will help determine whether such subsurface lakes are common features of icy worlds. Intergalactic stars drift far from any galaxy after tidal stripping. Not all stars reside within galaxies. A significant population of intergalactic stars drifts through the vast emptiness between galaxies, having been stripped from their original homes by gravitational interactions. When galaxies collide or pass close by, the tidal forces can tear stars from the outer regions and fling them into intergalactic space. These orphan stars now contribute to the faint intracluster light observed in galaxy clusters, a diffuse glow between the galaxies comprising perhaps 10 to 20% of the cluster's total stellar content. Individual intergalactic stars have been observed, including stars in the local group that appear to be between the Milky Way and neighboring galaxies. Their isolation is extreme. The nearest stars to an intergalactic wanderer may be millions of light-years away, compared to the few light-years separating stars within galaxies. Any hypothetical civilization on a planet orbiting such a star would look out at an almost completely dark sky, save for the faint smudges of distant galaxies. These lonely stars trace the dynamical history of the larger structures they now haunt, remnants of violent encounters that occurred billions of years ago. Some stellar winds are so powerful that they carve out vast bubbles in space. Massive stars, particularly those in the Wolf-Rayet phase, drive stellar winds so intense that they sweep up the surrounding interstellar medium into vast bubble structures called wind-blown bubbles. These winds can reach speeds exceeding 2,000 kilometers per second and carry away significant amounts of the star's mass over its lifetime. The swept-up material forms dense shells around the central star that can span tens of light-years, visible in images as glowing rings surrounding hot, luminous stars. When multiple massive stars in a cluster combine their winds, they can create superbubbles large enough to be carved out of the galactic disk. The most famous example in our sky is the Bubble Nebula, a 7 light-year diameter shell blown by the stellar wind from a massive central star. These wind-blown structures interact with the surrounding medium in complex ways, producing shocks, instabilities, and regions of triggered star formation. Eventually, when the central star explodes as a supernova, the shock wave will expand through the already evacuated bubble cavity, merging with the swept-up shell. Protostars accrete material through swirling disks of gas and dust. When a molecular cloud core begins to collapse under gravity, conservation of angular momentum causes the infalling material to flatten into a rotating disk surrounding the growing protostar. These protoplanetary disks serve as both the feeding reservoirs for the nascent star and the birthplaces of any planets that will eventually form. Material within the disk slowly spirals inward as viscous processes transfer angular momentum outward, eventually accreting onto the protostar and adding to its mass. This accretion is not steady but often occurs in bursts, causing the protostar to brighten temporarily when clumps of material fall onto its surface. The disk temperature varies with distance from the star, creating zones where different compounds condense and accumulate. Close to the star, only rocky materials survive, while further out, ices of water, ammonia, and carbon dioxide can persist. Observations of protoplanetary disks around young stars have revealed rings, gaps, and spiral structures that may trace the locations of forming planets clearing their orbital paths. Some galaxies experience bursts of star formation that consume gas rapidly. Starburst galaxies form stars at rates tens or hundreds of times higher than normal spiral galaxies, converting their gas reservoirs into stars at a pace that cannot be sustained for long. These extreme star-forming episodes are often triggered by galaxy interactions or mergers, which compress gas, shock it to higher densities, and funnel it toward the central regions where the starburst occurs. The resulting concentration of massive young stars produces intense radiation that ionizes surrounding gas and drives powerful winds that can expel material from the galaxy entirely. Infrared observations reveal many starbursts that are hidden behind thick dust cocoons, with the ultraviolet light from new stars absorbed and re-radiated at longer wavelengths. The most extreme starbursts occur in ultra-luminous infrared galaxies, systems so dusty that they emit most of their light in the far infrared. Starburst phases typically last only tens of millions of years before the available gas is consumed or expelled, after which the galaxy becomes quiescent. These intense episodes played a crucial role in building up the stellar mass of galaxies throughout cosmic history. High-energy photons from young stars ionize nearby nebulae. Hot massive stars emit abundant ultraviolet radiation that carries enough energy to strip electrons from hydrogen atoms in the surrounding gas, creating regions of ionized hydrogen called H2 regions. These glowing nebulae shine with the characteristic red light of hydrogen recombination, where freed electrons recombine with protons and cascade down through energy levels, emitting photons at specific wavelengths. The boundary between ionized and neutral gas, called the ionization front, expands outward as the young star's radiation progressively ionizes surrounding material. The resulting emission nebulae reveal the locations of recent and ongoing star formation throughout our galaxy and others. Different elements produce different colors when ionized, with oxygen contributing green and blue hues while nitrogen adds red, creating the striking multicolored images captured by modern telescopes. The ionization process also heats the gas, creating pressure differences that drive flows and sculptural features at the boundaries of the ionized regions. Each H2 region represents a temporary phase around young stellar clusters, lasting only a few million years before the hottest stars die and the nebula fades. Some moons contain complex geology shaped by internal heating. The moons of the outer solar system were once thought to be geologically dead, but spacecraft exploration has revealed surprising complexity driven by internal heat sources. Jupiter's moon Io is the most volcanically active world known, with hundreds of active volcanoes powered by tidal heating from Jupiter's immense gravity. Saturn's moon Titan hosts an active methane cycle analogous to Earth's water cycle, with rain, rivers, lakes, and atmospheric circulation. Europa and Enceladus show evidence of geologically recent resurfacing, with craters erased by icy tectonics and cryovolcanic activity. Even Triton, Neptune's large captured moon, displays geysers and terrain suggesting recent geological activity, despite its distance from the Sun. The internal heat driving this activity comes from various sources including tidal flexing, radioactive decay of heavy elements, and residual heat from formation. These geologically active moons have become prime targets in the search for habitable environments beyond Earth, as their internal heat maintains liquid water beneath icy surfaces. The diversity of geological processes on these worlds rivals and sometimes exceeds what we find on the rocky inner planets. Black hole accretion flares can vary dramatically over short timescales. The X-ray and optical brightness of accreting black holes can change by factors of hundreds or thousands over timescales, ranging from milliseconds to days, reflecting changes in the accretion rate or disk structure. These variations provide powerful tools for studying the inner regions around black holes, as the fastest changes must originate close to the event horizon, where orbital periods are shortest. Tidal disruption events occur when a star wanders too close to a supermassive black hole and is torn apart, producing a months-long flare as the stellar debris is accreted. For stellar mass black holes in binary systems, state transitions between distinct accretion modes produce dramatic changes in spectral properties and overall brightness. The most extreme variability is seen in blazars, where jets pointed nearly at Earth produce rapid flickering, as relativistic effects amplify small variations in the jet. Monitoring campaigns with space-based X-ray telescopes have revealed complex patterns of variability that encode information about the physics of accretion and jet formation. These flickering signals across all wavelengths tell us that black hole environments are dynamic places where conditions change continuously. Some exoplanets orbit so far out that their years last centuries. Direct imaging surveys have revealed exoplanets orbiting their stars at distances of hundreds of astronomical units, far beyond the orbits of any planet in our solar system. At these extreme separations, orbital periods stretch to centuries or even millennia, meaning we will never observe a complete orbit for these distant worlds. The planet Beta Pictoris b, orbiting at about 9 times Neptune's distance from the Sun, has an orbital period of approximately 2 decades, still relatively short compared to some of the most distant, directly imaged planets. How these far-flung planets formed remains unclear, as traditional planet formation models struggle to grow large bodies in the diffuse outer regions of protoplanetary disks. Some may have formed closer to their stars, and migrated outward through gravitational interactions with other planets or passing stars. Others might represent gravitational captures of originally free-floating planets. These distant giants challenge our understanding of planetary system architectures, and suggest that the full extent of planetary systems may reach much farther than our own solar system's edge. neutron stars spin hundreds of times each second. The most rapidly rotating neutron stars, called millisecond pulsars, complete hundreds of rotations every second, with equatorial surface speeds approaching a significant fraction of light speed. These extreme spin rates result from mass transfer in binary systems, where material falling from a companion star carries angular momentum that gradually spins up the neutron star over millions of years. The fastest known pulsar spins over 700 times per second, meaning points on its surface travel at nearly 70,000 kilometers per second. Despite their rapid rotation, millisecond pulsars are incredibly stable timekeepers, rivaling the best atomic clocks on Earth in their regularity. This stability makes them valuable tools for testing general relativity, searching for gravitational waves, and potentially navigating future spacecraft. The intense magnetic fields and rapid rotation combine to produce beamed radiation that sweeps past Earth like a lighthouse beam. Arrays of millisecond pulsars spread across the sky are being used to detect the low-frequency gravitational wave background from supermassive black hole binaries throughout the universe. The universe is expanding so fast, it may eventually tear itself apart. Observations over the past 2 decades have confirmed that the expansion of the universe is accelerating, driven by a mysterious energy component called dark energy that comprises approximately 70% of the total cosmic energy budget. If this accelerating expansion continues indefinitely, it will eventually overwhelm all other forces, potentially leading to a scenario called the Big Rip, where even atoms are eventually torn apart. In this fate of the cosmos, gravitational binding will be overcome on ever smaller scales, with galaxy clusters first separating, then galaxies themselves dissolving, then solar systems unraveling, then planets ripping apart, and finally, atomic nuclei. Current observations suggest the Big Rip is not the most likely outcome, but uncertainty remains about the precise nature of dark energy and how it will behave in the far future. Alternative scenarios include continued exponential expansion that isolates galaxies in their own cosmic bubbles, or eventual reversal toward a big crunch. Regardless of the ultimate fate, the accelerating expansion ensures that the observable universe will become increasingly empty and dark over trillions of years. The discovery of cosmic acceleration earned the 2011 Nobel Prize in Physics. Gravitational waves stretch and squeeze reality itself. Gravitational waves are ripples in the fabric of spacetime, produced when massive objects accelerate and propagating outward at the speed of light. When a gravitational wave passes through space, it alternately stretches and compresses distances in perpendicular directions, though the effect is incredibly tiny, far smaller than the width of a proton for realistic cosmic sources. The first direct detection of gravitational waves came in September 2015, when the Laser Interferometer Gravitational Wave Observatory detected the ripples from 2 merging black holes over 1 billion light-years away. Since then, dozens of similar events have been observed, including the merger of 2 neutron stars that were simultaneously detected in gravitational waves and light. The 2017 Nobel Prize in Physics recognized the scientists who made gravitational wave detection possible after decades of technological development. Gravitational waves open a completely new window on the universe, revealing events invisible to any form of electromagnetic radiation. Future space-based detectors will extend sensitivity to lower frequencies, revealing the mergers of supermassive black holes and perhaps even echoes from the earliest moments after the Big Bang. And now the quiet wonders of astronomy begin to gently fade into the stillness of the night. You have wandered through over 100 peaceful truths about the cosmos that surrounds you. From the explosive deaths of massive stars to the hidden oceans beneath frozen moons. From black holes that bend time to galaxies that collide in slow motion across millions of years. From the ancient light that has traveled billions of years to the dust grains that carry the building blocks of life. You have explored how stars are born in glowing nebulae, how planets form in swirling disks, how gravity shapes the dance of galaxies, and how the universe itself continues to expand into the unknown. You have learned that beneath every point of light in the night sky, there are stories unfolding that we may never fully see, all happening together in quiet cosmic harmony. You are connected to this story more deeply than you may realize. Right now, as you listen, the universe is doing what it has always done. Spinning galaxies, igniting stars, stretching the fabric of space, carrying ancient light across the void. It does not need your permission or your attention. It simply unfolds, patiently and silently, as it has since the very first moment of time. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the gentle pulse of starlight crossing the cosmos, like the quiet hum of a universe that never stops unfolding around you. Tonight, as you rest, the cosmos continues its quiet work. It will spin distant galaxies, birth new stars in glowing nebulae, send ancient photons on journeys that will last billions of years, shape new worlds in disks of dust and gas, and hold you gently within its vast embrace. You are a small, warm presence within this immense universe, peacefully resting among the wonders. Sleep well, sweet dreams. And may you carry with you the quiet knowledge that you are never truly alone, for the stars are always there, shining patiently through the darkness, keeping watch over the universe that gave you life. Thank you for joining me on this journey through the mysteries of the cosmos. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of how the universe works. There are more wonders waiting. More secrets hidden in the depths of space and the quiet corners of distant galaxies. More gentle truths to drift through on quiet evenings. Rest well, and may the ancient light of the stars keep you company through the night. This has been Drowsy Discovery. Good night.